Alright guys, are we all here? Yes, audible and visible everyone? Yeah, audible and visible to everybody? Okay, let's quickly go and call up your friends also. I just hope this does not happen. Why is this happening every single day at the same time? Yesterday also this happened after 1 hour. Today also this happened after 1 hour. It's so weird. That why is this happening? God knows why is this happening. Maybe I'll have to change my internet provider. Maybe then it will be better. Even yesterday this happened. That is why. I think I'll change my internet. Don't worry. I'll change my internet provider very soon so that this does not happen. Yes, I will take Henry's law. Don't worry. Don't worry. I'll take Henry's law once again. I am at exactly that, I'm exactly at that, what do you call it? That for real is a very good joke, yeah? Okay guys, quickly, little bit louder. I'm so sorry, bacha. I've already spoiled my throat. I will not be able to speak louder than this, okay? I suggest that please increase your volume. Please increase your volume. Yes, we are going to start. Can you quickly call up your friends? Because I see very less number of students. In the previous session, there were more students. Chalo, let's not waste any more time. Let us start with our session. Okay. So now today we are going to talk about, right now we're going to start from Henry's law. So once again everyone, what is Henry's law? I just told you that, okay, you know what, let me write this down here so that it is easier for you to understand, okay? The solubility of a gas, okay, the solubility of a gas in a liquid at constant temperature, okay, at constant temperature is directly proportional to the pressure of the gas present above the surface of liquid, okay, of the gas present above the surface of liquid or solution, above the surface or liquid of solution. Now do you understand this? What does it say? In other words, alternatively, you can write that the partial pressure of the gas in vapor phase P is proportional to the mole fraction of the gas X in the solution. Have a look at this. What does it say? It says that the partial pressure of the gas. The partial pressure of the gas that is just above the liquid, yes? So in the container, okay, understand it. So if I draw a container here and imagine that there is liquid here, if there is liquid here, then there is the gas phase, yes? Now this gas which is in the vapor phase, the gas is obviously in the vapor phase now, Baba. Of course, the gas is going to be in the vapor phase because this is the liquid. This liquid would have converted to vapor. So the gas is in the vapor phase. So the gas in the vapor phase, the partial pressure of this gas in the vapor phase, let's say is P, it is directly proportional to the mole fraction of this gas, which is X or chi in the solution. That means that this can be written as, everybody, mathematically we can write it as P is directly proportional to X. If you remove this proportionality constant, if you remove this proportionality sign, then you have to bring in a constant. And that constant is KH, which is called as the Henry's law constant, everybody. Is this clear to you all? Now is Henry's law clear to everybody? Now is Henry's law clear to everybody? Yes, guys. So then we are saying that now different gases, if you take nitrogen, Okay, nitrogen will have a different Henry's law constant. Oxygen will have a different Henry's law constant. Yes. So at the same temperature, different gases has different KH values. And this tells us that the KH, that is Henry's law constant, it's a function of the nature of the gas. That means the prime factor on which KH, that is Henry's law constant, depend on, it is the nature of the gas, everybody. Yes, everyone. Is this clear, guys? Is this clear? Is this clear? Yes. Is this clear? Anybody else who has a doubt with Henry's law, or do you understand this? Anybody else who has a doubt with Henry's law, or do you understand this? Do you need me to explain this again? Huh? Do you need me to explain this again, or do you understand this, everybody? Do we understand this, guys? Yes, new live stream, bacha, new live stream, because obviously the old one got messed up, so we had to do this. Yes. What definition? Sanvi, this is the second time I explain. You want me to explain this again? Explain again. Okay. All right, bacha. Explain it again. ठीक है. One more time. All right. Look at this picture, guys. Look at this picture. At this picture, right here, in the first case, what is happening? You have a container. In the container, you have liquid, okay? Liquid. The container also has a piston, but you are not using the piston, so the pressure right here is normal. Is this much understood? Is this much understood, everybody? Yes? Is this much understood? Is this much understood, everyone? No answer. Yes? Yes. So once again, everybody, you have a container. The container has liquid. It has a piston, but the piston is not in work. So normal pressure is here. This much understood. This liquid, whenever you keep a liquid, obviously some amount of the liquid will also be present in the gaseous phase, which is also called as the vapor phase, right? Which is also called as the vapor phase. So here, if there is a liquid, the liquid also exists in some amount of vapor phase. So this is your gas phase or vapor phase. Okay, this is your gas phase or vapor phase. Now, if we push the piston, that means if we apply some force and if we push the piston, that means force is increasing, pressure is also increasing. If force is increasing, then pressure will also increase, because the formula is force is equal to pressure by area. Force increases, pressure also increases. Yes. If pressure is increasing, you see that the gas molecules, the molecules in the gas phase, they are intermixing with the liquid phase. Do you see this? Yes. Do you see that they are intermixing with the liquid phase? Yes. Yes. So that means that we can say the solubility of this gas, the solubility of this gas in liquid, in the liquid phase, right here, this is what we saw. The solubility of the gas in the liquid, temperature here is constant, is directly proportional to the pressure applied. If you apply less pressure, less gas molecules will get mixed up. Yes, if there is more pressure, if you apply more pressure, that means that more amount of gas will be soluble in the liquid phase. Am I right? Am I right, everybody? Yes. Yes. So that is what we are saying. The Henry's law says that only, that the solubility of gas in a liquid at constant temperature, you are not changing the temperature, but you are applying some pressure, so it is directly proportional to the pressure of the gas that is present just above the surface of the liquid or the solution. Okay, all right. In other words, we can say that, now see, understand this. Together in this whole container, you have liquid and you have gas. So what will be our total pressure? Our total pressure will be the liquid phase pressure plus the gaseous phase pressure, right? Yes, that should be our total pressure, right? But we know that when we are talking about liquids, we do not really talk about pressure so much. So if we are talking only about the gas and the pressure that is exerted by the gas, can we call it to be partial pressure, because this is half of the pressure that this whole container is getting, is experiencing? Am I right? Am I right, everybody? So can I say that this is the partial pressure? Right. So this is what we are saying, that the partial pressure of the gas, which is in the vapor phase, obviously the gas is in the vapor phase, right? The gas cannot be in the liquid phase. The gas is in the vapor phase. Correct? So if we consider the partial pressure of the gas that is in the vapor phase, and let's call that to be as a P. If we call that to be as P, then we see that it is directly proportional to the mole fraction of the gas. What is the mole fraction of the gas? Chi or X, right? So we can write it as P is directly proportional to X. To remove this proportionality sign, we have to use a proportionality constant. And here we are using the proportionality constant as KH, which is called as Henry's law of constant. Yes. And when we look at the KH values for different gas, we see that it is different for different gas. That means that the KH value is strictly dependent on the nature of the gas. Now do you understand, guys, what is Henry's law? Please tell me yes. Now if you tell me no, I might have to I might have to jump off. Do you understand this, guys? Is this clear? Is this clear? Is this clear, everyone? Yes or no? Yes or no, guys? Yes or no? Is this clear? Okay. All right. Everybody understood. So the question now comes into your mind is that, but ma'am, why are we studying? Why are we studying Henry's law? Do we really require it? Yes. Application of Henry's law, if we check it out, we know that in the packing of soda cans, that is Coca-Cola. So when we're talking about Coca-Cola, what do? The Coca-Cola bottle, it is always it is packed under high pressure, so that we can increase the carbon dioxide solubility in the soda. Yes, that is what I was telling you from the beginning of the session. Yes, why do you think that you do not keep Coca-Cola bottles? Why are they not, why are they not kept in open bottle? They're not kept in open bottles ever. They're kept in this, strong sealed bottles, so that the pressure is more and you can make more carbon dioxide gas soluble. And that is why when you open it, everything comes out, like, it all comes out. Right, everybody? Yes. Very, very, very good. Okay. Now, in another, okay, so this is very, this is very normal day-to-day life that you have seen. But one more major important application of Henry's law, everybody, is nitrogen is actually more soluble than helium in our blood. Okay. All right. And when you have deep sea divers, they dive, right? And they go deep into the sea, isn't it? So the pressure is much higher. The pressure is much higher, isn't it? Under the water, guys. You understand this. How many of you swim? How many of you swim? If you swim, you must have noticed that the moment you put your head under the water, your ears start to fill with that that sound comes in, right? Why does it come? Because your ears are used to this pressure. They're not used to under the water pressure. So the pressure under the water is huge. Have you noticed? Recently there was this submarine where many of these very rich people, they went inside the submarine, and the submarine went like this. Did you guys read the news? Do you guys read the news, everybody? Did you notice that? Did you hear about this news, everyone? Have you noticed that, everybody? Did you see that? Did you notice the news? Yes, exactly. So what happened? The moment the submarine went under the water, they did not test it before. So what happened was, they were testing it outside the water and it was working fine. But the moment it went inside the water, it went pichik. Because the pressure is so much. Exactly. So the pressure under the water is much, much, much higher than the surface of the water. And when the diver, so they have dived, right? They have dived. Once they have dived, yes, the pressure is higher. But the moment they come up, to the surface of the water, what happens is the pressure decreases, and whatever is dissolved, the dissolved nitrogen, it comes back from the blood and it makes bubbles in the veins. Now that is very, very, very dangerous for us, right? And that is why divers, what they do is they use oxygen which is diluted with helium. Okay, they use oxygen which is diluted with helium, so that this does not happen, the bubbling in the veins does not happen. And this is a crystal clear picture of application of Henry's law, everybody. Yes, very good, absolutely right, Shailesh. The scuba diver, they suffer from bend, and a climber from anorexia. Yes, yes, yes. Anil Yadav, bacha, the channel name is JE Vedantu English channel. I cannot teach you in Hindi. Sorry, I cannot teach you in Hindi. This is an English channel. Okay, this is an English channel. Chalo. Yes, bends. Absolutely right. Bends. Yes. Okay, guys. Now let us talk about something that is vapor pressure. Okay. Ma'am, why does the cola fizzes out when we shake that? Is that related to solubility? Yes. When you are shaking it, what are you doing? You are actually exciting the molecules. Now the molecules are vibrating. The moment you vibrate, a little bit of temperature increasing is happening. The moment you increase the temperature, the gas tries to release out. The gas tries to escape out. So yes, it is related to solubility. Understood? Yes, understood? Yes. Yes, Riya. Yes, yes, yes. That is the correct answer. Okay? Okay. Sishira, no, bacha. Please don't feel bad, yeah. Sometimes take the joke, no? Please take the joke, bacha. Please take the joke. Please take the joke. Chill. Okay? I did not mind. Shailesh, wait. Okay. Now coming back to vapor pressure. Everybody, guys, let's not waste time. See, again, what if suddenly my internet goes off? I cannot do this again. So please let us understand. Now, what is vapor pressure, guys? So what happens is when you have equilibrium conditions, right? Equilibrium condition, you remember? In electrochemistry, in thermodynamics, you have read about it. In chemical kinetics, also you will read about it. KEQ, KC, KP, all of that. Equilibrium condition. Yes, very good, very good, very good. Yes. So at equilibrium condition, yes, the temperature is at equilibrium, the reaction is at equilibrium, right? What is happening? The pressure that you exert. Who exerts the pressure? You. No. The vapor. The vapor that is just above the liquid, that pressure that it is exerting, that is called as vapor pressure, bhai. That is called as vapor pressure. And at this point of time, when I said that equilibrium condition, see what is happening at equilibrium condition. The rate of forward reaction is supposed to be the rate of backward reaction. So that means rate of evaporation is supposed to be is equal to rate of condensation. Am I right? Am I right? Rate of evaporation is supposed to be equal to rate of condensation. That means it is equilibrium condition. At this point of time, that means that, okay, try and understand this. Imagine that I have a container here. I have a container here. And let's say that everybody, I have some liquid here. Okay, I have some liquid here. Yes. So this liquid, it will evaporate. This liquid, it will evaporate. And this liquid, when it evaporates, it forms some vapor. It forms some vapor. Yes. So that means this is what? Rate of evaporation. And when this vapor, it is getting converted to liquid, that means rate of condensation. Water vapor is getting converted to the liquid, right? So this blue color is rate of evaporation. And this red color is rate of condensation. Both of these are equal. This is your liquid phase. This is your, everybody, check it out, guys. This is your liquid phase. This is your vapor phase. Now both of them are at equilibrium. Now what is happening? This vapor phase, this red colored phase, this is going to exert some pressure on the liquid. And that pressure is called as a vapor pressure. That pressure is called as a vapor pressure. Are we clear with vapor pressure, everybody? Any doubt related to vapor pressure, everyone? Do we understand what is vapor pressure? No, Sabarish, you have to understand, okay? You have to understand, bacha. So when you have a warm tea, have you noted, acha, okay, now this is very basic. This is like a 6th or 7th class science that you are asking me, okay? But chalo, I'll still tell you. Have you seen the bottle of the Coca-Cola? How is the bottle of the Coca-Cola? It has a bottle neck, narrow neck, right? It is a narrow neck. The surface area at the top is very less. At this point, if you shake something, you are exciting the molecule. But when you take a teacup, surface area on the top is much, much huge, right? Then when you stir, what are you doing? You are uniformly trying to distribute the temperature. So when you are stirring at this point of time, you are not doing like this, right? Do you do this? You stir it. Nicely you stir it. At this point when you are stirring, you're trying to distribute the temperature. The heat is already getting released to the surrounding. When you are stirring it, you are just increasing that rate a little more. Getting my point? Getting my point, everybody? Shailesh, please read the sentence, no? Read the sentence, what is written here. Please read the sentence, what is written here. Do you see it? Yeah? Okay. Alright, everybody. Okay? Now, moving on from here, everyone. Now, moving on from vapor pressure, everybody. Let us move ahead from vapor pressure, guys. Can we? ये देखो आ गया अल्कोहल फिनॉल एंड ईथर, अल्कोहल फिनॉल एंड ईथर. बच्चा यार फिजिकल केमिस्ट्री कहाँ से कैसे पढ़ा दूं अभी अल्कोहल फिनॉल एंड ईथर. क्या कर रहे हो भाई? Yes, do we understand? Chalo. Now moving on from vapor pressure, guys, let us understand Raoult's law. This is the actual main important part of your chapter. So most of the questions will come from Raoult's law. Most of the questions will come from relative lowering in vapor pressure and all of that. That means colligative properties. So please pay attention, everyone. Guys, everyone, look at me, 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 and pay attention, everyone. Yes. Now, before we get into Raoult's law, everyone, let us talk about, let's say that you have a binary solution. What do you mean by binary solution, guys? What do we mean by binary solution? That means that we have two components, right? Binary. In your computer science also you learn, no? Binary language, 0 and 1. Computer only understands 0 and 1, right? ASCII value and all of this. It is always in 0 and 1. It isn't binary. Yes, absolutely. So suppose, okay, 1 second, sorry. So suppose you have a container here, okay? You have a container here. And in this container, what have you done? In this container, what have you done? You have a binary solution. Guys, writing this down, everybody, so that you clearly understand, okay? You have a binary solution of two volatile liquids, okay? You have a binary solution of two volatile liquids. Yes? Volatile, do you understand what is volatile, guys? Volatile basically means liquids that can evaporate very fast. The liquids that can react very fast. For example, alcohol and acetone. Alcohol and acetone, both of them can fly very well, isn't it? Sanitizer, if you put it on the table, it evaporates and goes away, right? It evaporates and goes away. So basically, you have component 1 and component 2, or component A and component B. Okay? Alright? Yes, everybody. So let us say, I'm writing it down here. Yes, you have component 1 as well as you have component 2. Okay? Now here, this is, let's say, your liquid phase. This is your liquid phase. Okay? Alright? And here, my dear students, here you also have the vapor phase. Okay? This is your vapor phase. Okay? Now, both the components, they will evaporate because they are volatile. I have just told you. Because they are volatile, both of them are going to evaporate. And when they are evaporating, we are also assuming that eventually there will be a time when there will be equilibrium that will be established, right? Yes, everybody? Correct, everyone? There will be a time when the equilibrium will be established. But equilibrium will be established between whom? The equilibrium will be established between this liquid phase and the vapor phase, guys. Right? So at this point of time, what is going to be my total vapor pressure, guys? What is going to be my total vapor pressure? So let me write it down that total vapor pressure is going to be P total. Right? Let us write that P total. Now, the pressure that is exerted by component 1, that will be P1. So P1 can be my partial partial vapor pressure of component 1, right? And P2 can be partial vapor pressure of component 2. Am I right, everybody? Am I right here? And this partial vapor pressure P1 and P2, they are related to the mole fraction Chi1 and Chi2. Am I right, everybody? Am I right, guys? Do you understand this much? This is the very basic of Raoult's law. If you do not understand this, it is going to be tough. Everybody, can I, guys, please focus up. Concentrate here. What and all you are chatting in the chat box here? Concentrate here. What do we have, guys? We have here a container. In this container, you have component 1 and component 2. Both of them are volatile liquids. They are going to be in equilibrium after certain point of time. That means the liquid phase and the vapor phase, both of them are going to be in equilibrium. At this point, what is going to be my total vapor pressure? That can be written as P total. Now, P1 is going to be the partial vapor pressure of component 1. And P2 is the partial vapor pressure of component 2. This P1 and P2, they are obviously related to Chi1 and Chi2. That is the mole fraction. Where, from, how did I derive this? How did I derive this, everybody? Can you please tell me? Can you please tell me, everybody? P1 and P2 are related to Chi1 and Chi2, the mole fraction. Where did we get this from? Henry's law. Yes. From Henry's law, we know that P is equal to KHX. That means they are related to the mole fraction. Yes, very good. Now from here, guys, we want to understand the Raoult's law. So Raoult's law, it suggests that for a solution of volatile liquids, the partial vapor pressure of each component of the solution is going to be directly proportional to mole fraction present in the solution. But that was Henry's law, no? That was Henry's law, isn't it? Isn't it? But chalo, let me write that down just so that we try and understand it a little better, okay? See, here he is writing for a solution of volatile liquids. For a solution of volatile liquid, everybody, take a look at it. For the solution of volatile liquids, the partial vapor pressure of each component of the solution is directly proportional to its mole fraction present in the solution. Mole fraction present in the solution. There is a difference from Henry's law, everybody. Here he is writing PA is directly proportional to Chi A. Yes, or XA, everybody. But this, if we remove this proportionality sign, we will write it as PA is equal to Chi A multiplied with PA naught. Now, what is PA naught, everyone? What is PA naught? So, guys, here we had a container where we had a solution. But before we made this container, do you all agree with me that we probably had a container, we probably had another container? In this case, we had component 1. Right here, we had component 1. And right here, we had component 2, right? Yes. So this component 1, when this was evaporating, there was some pressure that this vapor phase of the pure solvent was exerting. What do we call that? That will be called as P1 naught or PA naught. PA naught is the pressure of pure solvent. Pressure of pure solvent, everybody. Getting it? Similarly, here the component 2 will also be exerting P2 naught or PB naught. This is also pressure of pure solvent, everybody. Yes? Alright? Absolutely. So now if I check it out, see what is happening. See what is happening, everybody. PA is equal to partial vapor pressure of component A. PA naught is the vapor pressure of pure component A at a given temperature before you mixed it up and made it into a solution. Yes, before you mixed it up and made it into a solution. So this, my dear student, becomes your Raoult's law, everybody. Do we understand this? Yes, very good, Angeline, very good. So similarly, for now liquid B, for the liquid B also we can write it, right? PB is equal to chi B PB naught. Yes, chi B PB naught, I can write it. So then from Dalton's law, what did Dalton say? What did Dalton say, guys? Now Dalton said that, okay, let me write this down for you guys. Okay, Dalton's law, everyone, here. Dalton's law, everybody. The total pressure, that is P total, yes, over the solution phase, okay, over the solution phase in the container, will be the sum of the partial pressures, will be the sum of the partial pressures of the components of the solution. All right, so that means we can write here that P total is equal to PA plus PB. That means we can write it as chi A PA naught plus chi B PB naught. Can we do that? Yes, of course we can do that. Yes, of course we can do that. But tell me something, everybody. If I'm writing it like this, then don't you think that I can also write it as this chi A, remember from mole fraction, chi A plus chi B is supposed to be is equal to 1, right? So that means that chi A is equal to 1 minus chi B, am I right? So let me write it here that 1 minus chi B multiplied with PA naught plus chi B PB naught. Can I write it like this? Can I write it like this, guys? Yes, I can. Now from here I can also write it as PA naught plus, I'm writing here plus, okay? Then I can write it as PB naught minus PA naught multiplied with chi B. Can I write it like this? Can I write it like this? Can I write it like this, bacha? Yes, I can. Yes, I can, everybody. So this, my dear student, is the derivation of Raoult's law from Dalton's law, everybody. Do you get it, guys? Yes, do you get it, everybody? Do you get it, guys? Yeah? Do you get it, everyone? Now, let us continue talking about vapor pressure. So what is vapor pressure? We have understood that the pressure exerted by the vapor of liquid which are in equilibrium with it at a given temperature. This is not a surface phenomenon, by the way. This is not a surface phenomenon, and it increases with temperature. Okay? It increases with temperature. All right? Yes, everybody. Do we understand, guys? Do we understand this? Yes or no? After this, there is ideal solution, Raoult's law here. We're almost done with the chapter, guys. After ideal solution, we will be quickly taking a look at the colligative properties, and after that, we are going to solve some question. Or should we solve some question and then come back to it? Acha. Now, but before I move forward with the questions, I want to do one thing, okay? Here, guys, this is very important. Now, listen to me. Now, if I say that liquid solution, you have a liquid solution containing, okay, you have a liquid solution which contains non-volatile solute. Non-volatile solute. If I say non-volatile solute, guys, will you agree with me if I say that this is a solid liquid system? Will you all agree with me if I say that this is a solid liquid system? Because non-volatile solute, if it is a liquid, then it will definitely get into a vapor phase. So it cannot be called as a non-volatile. When I say non-volatile, we mean here this is a solid liquid system, everybody. This is a solid liquid system. At this point, the solid is definitely not contributing towards the vapor phase at all. Am I right? The solid is not at all contributing towards the vapor phase at all. That means that there is no pressure that is exerted by the solid at all. So can I say that, everybody, that vapor phase or vapor pressure of liquid solution, vapor pressure of liquid solution is directly proportional to the mole fraction of solvent, in liquid solution. Can I say that? Of course I can. That means that the P solution can be directly proportional to chi of solvent. Yes, of course I can say that. If that is the case, that means that my P of solution is equal to P naught of pure solvent multiplied with chi of solvent, that means mole fraction of the solvent. Yes. So that means here, what is chi of solvent? Chi of solvent is the mole fraction of the solvent. P naught of solvent is the vapor pressure of the pure liquid of the solvent. Correct, everybody? Correct, everybody? Do we guys understand this? Everyone? Yes or no? Yes or no? Now, guys, if let's say that we want to draw a graph, okay, let us say that we want to draw a graph for Raoult's law, especially for a binary liquid solution where you have solute plus solvent. Yes, where you have solute plus solvent, we want to draw a graph. How do I draw the graph, guys? Let us draw the graph like this, okay? First of all, we will make a container shape like this. So imagine if I say that chi of A is equal to 1. Once again, reminding you, everybody, do you all know that chi A plus chi B is equal to 1? So if my chi of A is equal to 1, that means obviously chi B is equal to 0. That means mole fraction of the B component is going to be 0. Yes? Yes, agreed, everybody? Great. Okay. So that means that now after some time, what will happen? Chi A is equal to 0. If mole fraction of A is equal to 0, that means obviously mole fraction of B is equal to 1. Very good. Okay. Now here, what am I going to get? I will be getting here, let's say this is my PA. This is my partial pressure by A. This will be called as PA naught. That is the pressure of the pure solvent. Here P total is equal to PA. What we just did. For a solid liquid system. This is the graph that you make, okay? For a solid liquid system, this is going to be your graph. Guys, 100% do we understand? 100% do we understand, everyone? 100% do we understand? Any doubt related to all of these? Guys? 100% do we understand, everybody? Yes? Yes, everybody? Yes? Yes? Yes, do we understand? Great. Okay. All right, everybody. Now, before composition of vapor phase, guys, this is also, see, what we are doing here is we are taking YA and YB. All these while we were taking chi A, chi B. Chi A, chi B is what? XA, XB, that is the mole fraction of A component, B component. Now, A component and B component are in liquid. If they get into vapor phase, let us suppose that YA and YB are the mole fraction of vapor phase. Okay? Mole fraction of component A and B in vapor phase. Now we know that PA is equal to YAPT from Dalton's law. That means that PA is equal to XAPA naught from Raoult's law. That means, can we equate it? Of course we can equate it. No, of course we can equate it, right? Of course we can equate it. So we will write PA is equal to YAPT is equal to XAPA naught. That means chi APA naught. Yes, everybody. PB is equal to YBPT, which is equal to XBPB naught. We also know that XA plus XB, that is equal to 1. So that means, everybody, everyone, that see, YAPT divided by PA naught plus YBPT divided by PB naught. That means, okay, handle, everybody. Guys, are you able to understand this or no? Or should I write it down again? Should I write it down again or are you able to understand it? Not able to understand it? Chalo, I'll write it down. I'll write it down. Okay? Okay. Everybody, once again listen to me. Okay? So we know that XA and XB are what? Mole fraction. Mole fraction of liquid phase. Right? Mole fraction of liquid phase. Let us suppose that YA and YB, everyone, YA and YB is mole fraction of vapor phase. ठीक है? This much is clear? This much is clear? This much is clear, guys? Yes? Okay. Now everybody, from Dalton's law, we know that PA is equal to Y of A multiplied with P total. This is Dalton. This is what Dalton said, right? Right, everybody? This is what Dalton said. This is what Dalton said, guys. Guys, yes or no? Please tell me. Is this your Dalton's law? Dalton said that PA is equal to vapor pressure multiplied with P total. Right, everybody? Now, what did Raoult say? Raoult said that PA is equal to mole fraction in liquid phase multiplied with vapor pressure of the partial pressure of the pure solvent. So this is what Raoult said. This is what Raoult said. Right, everybody? Yes or no, guys? I cannot see any chat here. Yes, guys? Yes? Sabarish, please, yeah, rewind and check it out, bacha. I cannot do this, seriously. 5 o'clock, Nandini ma'am is supposed to take organic chemistry. I have to finish this before that, okay? Can you please rewind and watch it again? Can we please rewind and watch it again? Because if I take it again, it will be too much of a delay and I have to finish 3 chapters today anyhow, okay? Alright, everybody? Vignesh, did you understand or not, guys? Yes or no? I'm losing hope now. Don't feel like teaching you guys at all. Somebody please say something. I'm still not able to see your chat. Understood? Clinical clear. Okay. Okay. All right. Yes. Okay. Now, from this Dalton, what Dalton said and from what Raoult said, we can equate this, right? Because see, PA is equal to both the places it's PA. That means we can write it as YAPT is equal to XAPA naught. Clear? Right? We can do this. Yes, we can do this. Very good. Okay. Now, that means that we also know, everybody. So we also know, guys, tell me something. Don't we know that if YAPT is equal to XAPA naught, that means that YBPT is equal to XBPB naught. Can I say that? Can I write that? Yes, I can. Yes, I can. Yes. Now I know that XA plus XB is equal to 1 because this is mole fraction. If you add on all the mole fraction, that means that what is it? Is equal to 1. It is equal to 1. Am I right, everybody? Am I right, everybody? Yes. Very good. Okay. So, from these formula, from this and this, what can I write for XA, guys? XA can be written as YAPT divided by PA naught. Can I write it like this? Can I write it like this? Yes, I can. What will be my formula for XB? XB can be written as YBPT divided by PB naught. Am I clear? Now from this formula, I can write it as YAPT divided by PA naught plus YBPT divided by PB naught. Yes, I can do this, right? Now I know that PA naught and PB naught, if I add, what will I get? I will get P total. What will I get? I will get P total, correct? So this means that I can write it as or P total, I can take it common, right? I can write it as P total multiplied with YA by PA naught plus YB divided by PB naught. I can write it like this. That means that 1 divided by, see, check it out. That means that 1 divided by PT is equal to YAPA naught plus YBPB naught. Do you understand? Yeah, I have moved it. Last line. Yeah. Moved it. Moved it, guys. Moved it, yeah. Now do you understand this? Yes? Now do you understand this? Yeah, you do? Exactly. So this is your composition of vapor phase. Once again, it's just a derivation and it's probably not there in your NCERT, but I think that you should know it, okay? I thought that you should know it. Chalo guys, moving on now. Moving on everybody, okay? Now let us talk about types of solution, and firstly we come across ideal solution, okay? Firstly, we come across ideal solution. Bachu, once again, Adit, can you please go back and watch it? If I keep repeating the same thing again and again, it will take me a lot of time. I will not be able to finish it before 5 p.m. Okay? 5 p.m. you have organic chemistry classes. Before that, I have to finish all the 3 chapters. So please pay attention and don't do this. Okay? And no breaks today. Chalo. So ideal solution. What are ideal solution, guys? Now, ideal solution are those solution, as per the definition, it says that it obeys Raoult's law, okay? What does ideal solution do? Ideal solution, they obey Raoult's law, but not for just a minimal amount of time. They obey Raoult's law over the entire range of concentration. Throughout the range of concentration, they are going to obey Raoult's law, everybody. Yes? Now, here what are we saying is that, so imagine you have a component A. You have a component A, you have a component B. Yes? Now, component A will have A type of molecule, right? Component A will have A type of molecule. Component B will have B type of molecule. So the AA interaction in the component A and the BB interaction in the component B is something that you can see in this picture. When you mix it, what will happen? The solute and the solvent molecule, that means there will be AB interaction. Are you getting it, everybody? Are you getting it, everyone? Yes or no? Yes or no, everybody? Yes or no? Yeah? So we are saying that whatever we calculate, P total is equal to PA plus PB. That is what we know from Raoult's law, right? That is what we know from Raoult's law. Now, if we observe it, let's say that we have observed P total, that should be equal to PA plus PB calculated. PA plus PB calculated. That should be equal. Only then we will say that this solution is ideal. That means that when you mix this two, what will happen? The volume should not increase. Yes. How is that possible, right? It's ideally not possible. So what is happening? The volume should not change at all. The enthalpy, when you are mixing something, there should not be any enthalpy change at all. All right? There should not be any enthalpy change at all. All right, everybody? So this is what we are saying in case of an ideal solution. Rare, bacha, why? Why? Do you seriously want me to cry and change my profession altogether? Because you are trying to make me do this. Why? Why are you doing this? What is wrong with you? Whatever is there in your NCERT, I'm teaching you, know. Once I've moved from that, then suddenly you come and you start spamming the chat box. What are you doing? What are you doing, bacha? Trying my best to not look at the chat box, but you will spam and make sure that I see it. And then all the other students will be like, ma'am, don't look at the comment section, ma'am, don't be negative, ma'am. Why? I've taught you chill. Spamming again and again, ma'am, this relation, ma'am, this relation, ma'am, this relation. Arey Baba, teaching you whatever is there in your syllabus. Chill. Constantly spamming. Now, once again, everybody. So, let us suppose that, okay, so if I have water bottle here, right, and I expect that this is my A type of component, okay, this is my A type of component, right? In this A type of component, what do I expect? I expect that the water molecule, they are going to interact. Yes, very good. If I have a B type of component, then I expect that B and B, they are going to interact, isn't it? Now what is happening is the AA and the BB interaction are supposed to be equal to when you mix them and you have AB type of when you have mixed them. Now the interaction between AB should be equal to AA and BB type of interaction. Understanding, everybody? Understanding, everyone? Yes? Understanding, guys? Correct or not? Everybody? Now, ideal solution example, everybody. Yes, ideal solution example, guys. Do you guys know any example? Okay, now can I look at the chat box, everybody, and tell me what are the ideal solution examples? Some examples from your NCERT, everybody. I know it is there, and I know one of the most famous organic chemistry compound that we read about. So quickly go ahead and let me know. Quickly go ahead and let me know, everybody. Some examples of ideal solution. Some example of ideal solution, guys. Upper standing, acha, okay. Very nice. I showed you, did I not? Nothing is ideal. Nothing is ideal, it seems. Sigma, absolutely right. Absolutely right, yes. Clap everybody. Clap for yourself, guys. Clap for yourself. Very good. Benzene and toluene, N-hexane and N-haptane. Yes, very good. Awesome. Okay. So now, what are the properties of ideal solution, everybody? Raoult's law is obeyed. Delta H mix is equal to 0. That means when you mix it, the enthalpy should not change at all. There should not be any enthalpy change of the components of ideal solution. Delta V mix is 0. That means the volume should not change after you mix it. And that only happens in case of N-hexane, N-haptane, ethyl bromide and ethyl iodide, benzene and toluene. Okay? Yes, guys. That is the correct answer. Okay? That is the correct answer. Now, guys, what are non-ideal solution? Non-ideal solution, obviously something that does not obey the Raoult's law. They are going to be non-ideal solution. That means that the AA interaction, the BB interaction, these interactions are not equal to the AB interaction. Now, either what can happen is the AA interaction, the BB interaction is greater than the AB interaction. Yes. Or there is a possibility that the AA interaction, the BB interaction is lesser than the AB interaction. That is also possible. That is also possible. Exactly. Now, based on this non-ideal solution, based on how they follow the Raoult's law, we have positive deviation and we have a negative deviation. Okay? We have positive deviation and we have negative deviation. So, what is positive deviation? When do we have positive deviation? We have positive deviation when we have the AA interaction, the BB interaction. This is greater than the AB interaction. That means that when you mix them, they don't want to be together. They don't want to be together. For example, everybody, let us suppose that all of you are students, all of us are teachers, right? Now, So I would like to be friends with Namrata ma'am, Nandini ma'am and Shreyas sir more than I want to be friends with you, right? I mean, usually, understand this, understand the story, everybody. So let's suppose that we are the B components. Teachers are the B components in the class. And you guys, you would want to be friends with other students of your class, right? Am I right, everybody? Am I right, everybody? Yes. So if you mix us, if you put two students and teachers together for one exam, or let's say if you put students and teachers in one class, what will happen? I will have an affinity that no. I want Nandini ma'am, Namrata ma'am and Shreyas sir. And you guys will be like, no, we don't want to hang out with ma'am. Ayyo, it's so awkward. Ma'am is trying to be all cool and all, but she's not cool like us. Right? She's not cool like us. I mean, obviously, I'm older than you. I'm not going to be as cool as you. You guys will know about a lot of other things like Snapchat and Free Fire and PUBG and GTA and all of these. I do not know. I don't play all of these. So, our interactions are not going to be equal. So if you mix us, I would want to not be with you. You would want to not be with me. And you will obviously want to be with your student and I would want to be with the teachers. That is your positive deviation. That is your positive deviation. You getting my point? You getting my point, everybody? Yes. But now imagine there is negative deviation. That means that now all of you, let's say that you are all from school, okay? You're all from school. Or let's say that you go outside to a mall, okay? Let's say that you go to a mall and once you go to a mall, you find, okay, so let's say that you are going to mall with us. Let's say that you are going to the mall with the teacher. So this was our AA interaction because we all belong to Vedantu. So this was our AA interaction. We are all Vedants. We are going to the mall, okay? And suppose you have a different set of students coming into the mall and they are doing BB interaction. But the moment you enter the mall, you see that, I to know them. They are all from your society. They are all from your school. Now what will happen? Now your interaction will be more, isn't it? Right? You would want to hang out with your school and your society friends more. So now what is happening? The mixing, the AB interaction is more than the AA and the BB interaction. Are you getting it? So this will be negative deviation. Guys, how many of you understood the story? How many of you understood the story, everybody? How many of you understood the story, everyone? Did anybody understand the story? Hello. Hi. Hi, everybody. Thank you, Luxury Hitler. EPBT, anybody else who understood the story, or do you want me to repeat this again now? Yes, exactly. So in the positive deviation, the interaction between AB is not so much, right? The interaction between AB is not so much. But in the negative deviation, you see suddenly that what happens is the AB is interacting more, okay? AB is interacting more. All right, everyone? Yes, everybody? No, you did not understand. How many people did not understand? If you did not understand, forward it and watch it. Okay? So here what happens is that for positive deviation, the P total is greater than PA naught chi A plus PB naught chi A, everybody. Okay? Alright, everyone? Yes, guys? Yes? Very good. Okay. Alright. In case of positive deviation, we see that delta H mix, it is greater than 0. Delta S mix is greater than 0. Delta V mix is greater than 0 and delta G mix is lesser than 0. This is what we see in case of positive deviation. Okay, this is what we see in case of positive deviation. Am I clear, everybody? Yes, am I clear, guys? Am I clear, everyone? Yes. Now, in case of positive deviation, if we want to make the graph, yes, how will we make the graph, guys? How will we make the graph here? This is how we will make the graph. See, check it out. Yes, this is what it is. So first of all, obviously here we will write XA is equal to, let's say 1. That means that XB is equal to 0. And here XA is equal to 0. That means XB is equal to 0. Now ideal solution, in case of ideal solution, we know that this is our PA naught. This is our PA naught, yes, and this is our PB naught, right? Ideally, and this is our P total, correct? But now what we see in positive deviation is that this swells up like this swells up like this, and this also swells up like this. This is the graph, okay? This is the graph for your positive deviation. All right, everyone? Yes, guys. Moving on now, everybody. Yes, okay. So these are all the things that I've already written it down. I've told you this. Now somebody was asking me examples. So bacha, here are all your examples. You see chloroform and water, ethanol and CCl4, methanol and chloroform, benzene and methanol, acetic acid and toluene, acetone and ethanol, methanol and water, C2H5OH, what is it? Ethanol plus cyclohexane, okay? Cyclohexane, these are your positive deviation from Raoult's law. Yes, okay? Alright, moving on, guys. Now let us talk about negative deviation. That story also I have told you what is negative deviation. In negative deviation, P total is going to be lesser than PA naught chi A plus PA naught chi B. Alright. And here we expect that delta H mix is lesser than 0. Delta V mix is lesser than 0. Delta S mix is greater than 0. And delta G mix is lesser than 0. This is going to be the same for everything, okay? This is going to be the same for everything. All right, everybody? Yes. So here, how is the graph going to look like, guys? Here the graph is going to look like, see, I'm going to draw the graph. I'm going to draw the graph right here. Yes, again, once again, everybody writing it down. XA is equal to 1, XB is equal to 0. So here XA is equal to 0, XB is equal to 1, right? Ideal scenario, our graph should look like this, right? Our graph should look like this. So this is our PB naught, this is our PA naught, and this, my dear student, is your P total. Now here, because of negative deviation, you see that P total has decreased like this. This has also decreased like this, and this also curved like this. So this is your graph for negative deviation. Yes, bacha, graph. Yeah, showed you graph, hai na? Now from here, what do you see? What are the examples? Chloroform and methyl acetate, H2O and HCl, H2O and nitric acid, acetic acid, pyridine, phenol and aniline, acetone and chloroform. Alright, everybody, these are the only things that you have to remember. Alright, these are the only things that you have to remember. Cool, everybody? Yes, bacha, moved it. Clear? Now we come across something that is called as azeotrope. Somebody had asked me in the last session that, ma'am, what is azeotrope? What is azeotrope? So let me tell you, azeotropes are those mixtures with constant boiling. They have the same composition in the liquid phase as well as in the vapor phase. Okay. Now what is minimum boiling azeotrope? Non-ideal solution which boil at lower temperature than the boiling point. For example, if you take ethyl alcohol and if you take 4.5% of water at mass, and if you try to boil it, you will see that the boiling point of water has decreased down. In fact, the boiling point of, not water, you will see that which boil at a lower temperature than boiling point of each component in the pure state. Boiling point of water, here it will be lesser. Boiling point of ethanol, here it will be much lesser than that also. Okay, much lesser than that also. Cool, everybody? Clear? What is maximum boiling azeotrope? Non-ideal solution that boil at a higher temperature than the pure solvent, that is called as maximum boiling azeotrope. For example, here you have nitric acid and water. Both of them together, if you mix it, they are going to be higher temperature. They are going to boil at higher temperature than this. Alright, everybody? Got it, guys? Clear? Chal. And these are the graph of maximum boiling and minimum boiling azeotropes, everybody. Now let us quickly go to colligative property. What are colligative property, everyone? The colligative property, my dear students, are those properties of the solution which does not depend upon the nature of the solute. Okay, they do not depend upon the nature of the solute, but they depend on number of solute particles, everybody. So how many colligative properties do you have? You have 4 colligative properties. Number 1, relative lowering in vapor pressure, that is called as RLVP. Number 2, elevation in boiling point, that is called as EBP. Depression in freezing point, that is DFP, and finally osmotic pressure, that is OP. So everybody write down some OP in the chat box. Now let us quickly start with relative lowering in vapor pressure, and that is, so when you have two non-volatile solute, yes, vapor pressure of a solute, let's say that you have two non-volatile solute. Sorry. You have a non-volatile solute and you are adding it to volatile solvent. Cool. That means both the components of the solution are volatile. Understanding everybody? Understanding everybody? What did I say? You have a non-volatile solute. What am I saying? Sorry, I got this thing. I got distracted. Sorry. Yes, thank you so much. OP. सारी डेरिवेटिव्स याद कर ली मैम, पास हो जाओगे? पास हो जाएगा क्या? क्या पता, पढ़ना तो सब कुछ होता है, सिर्फ डेरिवेशन से थोड़ी हो जाता है. Vitesh, what are you asking? Vitesh, what are you asking? Any other example given how to predict it is positive? No. That's it. This is what you learn. You can also check it out in NCERT. This is how you predict it. But you don't have to predict it because generally they will not ask you if this will show positive deviation or negative deviation. Yes? You have to remember the examples. Okay? Yes, Vitesh, I've just told you. When are we having PYQ? Just after this, just after solving this, we will solve some PYQ. Okay? Yes. Okay. So now everybody, you have a non-volatile solute. That means solid you have added to a volatile solvent. Solid in liquid system. The vapor pressure decreases. Okay? You see that the vapor pressure decreases. So everybody try to understand what I'm saying. I'm saying that you have a component. Let's say that this is your liquid solvent. Okay? And this is our volatile component. Okay? That means that we also have B component. The B component is your solid solute. Yes. And this is your non-volatile. Right. Now everybody tell me what is P total. P total can be written as, that means it is P of A only, because this is solid solute. The solid solute is not going to contribute towards the partial pressure, can it? Will it? Will it? It won't, right? It will not. It will not be able to contribute to the partial pressure at all. So if that is what I'm writing, now my PA can be written as, what is PA? PA can be written as PA naught 𝐸𝐴. That means this can be written as a PA naught 1 minus 𝐸B. Can I do this? Of course I can. Now this PA is what? Liquid solvent. So can I write it as PS is equal to PA naught minus PA naught 𝐸B. Can I write it like this? Yes, I can. Yes, I can. So from here, I see that I can also write it as PA naught 𝐸B is equal to PA naught minus PS. Can I do that? Yes, I can. If I write it like this, everybody, now tell me, from here I can also find the mole fraction. Mole fraction can be PA naught minus PS divided by PA naught. And this, my dear student, is your relative lowering in vapor pressure. This is your relative lowering in vapor pressure, everybody. Now this part, everybody, this right here, what I wrote here, everybody, what did I write? I wrote that 𝐸B is equal to PA naught. Now PS that I wrote, can you notice that PS and PA are same? PS and PA are same. If that is the case, that means I can write it as PA naught minus PA divided by PA naught. And this particular part can be written as delta P divided by PA naught. Can I do this, guys? Can I do this? So that is my mole fraction of B. And from here, I also know that mole fraction of B can be written as number of moles of B divided by number of moles of A plus number of moles of B. Am I right? Is this derivation easy peasy? Is this derivation easy peasy? Yes, it is. Yes, it is. Now we come across boiling point, everybody. What is boiling point, everyone? Boiling point is the temperature at which the vapor pressure becomes equal to atmospheric pressure. That is called as your boiling point, right? What is boiling point, everybody? Chalo, let me write down the definition of boiling point also, just for your sake, everybody. Temperature at which vapor pressure, that is Vp, becomes equal to the atmospheric pressure, that is 1 atm, that is called as boiling point, everybody. So now if I have to draw the graph of the boiling point, everyone, how do we draw it? Yes, how do we draw it? I'm going to draw it as, let's say this is your temperature. Yes, this is your temperature. Let's say that this is your 273 Kelvin, that is 0. Yes, here everybody, right? Now here what is happening? Vapor pressure is increasing, everybody, correct? So from here I will see that this is how it increases, and right here if I draw a line, then I see that this is your 373 Kelvin, that is 100 degrees Celsius. Yes, so this is my normal boiling point. This is my normal boiling point. But now we want to talk about elevation in boiling point. Now we want to talk about elevation in boiling point. That means that the boiling point has increased. When does that happen? When you have a non-volatile solute and you have dissolved it in a volatile solvent, everybody, right now we saw what happened. The vapor pressure decreases. If the vapor pressure decreases, then the boiling point will increase, isn't it? Huh? If the vapor pressure decreases, then the boiling point is going to increase, isn't it? So what we see is that we see this kind of a graph. Here you have the pure solvent. Yes, my dear student, this is your pure solvent. And when you have the solution, you see that this is your delta TB. That means this is the elevation in boiling point. That means this is the increment in the boiling point, everyone. Okay? And what is the formula for elevation in boiling point, everyone? What is the formula? We all know that TB is proportional to M, that is molality, which if we remove the proportionality sign, it will be written as TB is equal to Kb multiplied with M. Basically, what is Kb? Kb is the molar elevation constant or ebullioscopic constant, everybody. Okay? Alright, everybody? Yes, guys. Okay, now moving on from here, everybody, now you see that if you want to find out Kb, what is Kb? Usually it is given to you. If it is not given to you, then this is how you find out. This is the formula. RTB square, capital M, that is molarity, divided by 1000 multiplied with delta H, vaporization. Or you can directly write it as RTB square divided by 1000 into L vaporization. L vaporization is latent heat of vaporization, everybody. Cool? Then we come across freezing point, everybody. What is freezing point, guys? Freezing point is obviously, can you write this down, everyone? Freezing point is a temperature at which vapor pressure, okay, temperature at which vapor pressure of solid becomes equal to vapor pressure of liquid. That is called as freezing point of liquid. And what is depression in freezing point? So when we notice that when you mix a non-volatile solute and dissolve it into a volatile solvent, you notice that vapor pressure decreases, and so does the freezing point. Yes, the freezing point also decreases, and that graph can be seen right here, everybody. This is your delta TF. What is delta TF, guys? Delta TF is the depression in freezing point. And once again we know that delta TF is proportional to molality. That means that delta TF is equal to Kf multiplied with M. What is Kf? Kf is your cryoscopic constant, everyone. Okay, Kf is your cryoscopic constant. Cool, everybody? And similarly you can calculate it for cryoscopic constant Kf right here, everybody. Same formula, RTF square divided by 1000 multiplied with L of fusion. That is latent heat of fusion, everybody. Okay? Alright, everyone. Yes, depression in freezing point. Very good, everybody. Last but not the least, everyone, what is osmosis? Osmosis is basically the phenomenon or the incident where what happens? The passage of pure solvent into solution, or less concentrated to more concentrated, when through a semi-permeable membrane something is traveling. That's called as osmosis. Now if I apply some pressure and make sure that the osmosis stops, if I apply pressure and osmosis stops, that will be your osmotic pressure. The excess pressure that you apply to stop the osmosis, that's called as your osmotic pressure. And that, my dear student, is given as pi is equal to CRT, where C is molar concentration, T is temperature, R is gas constant. Okay. If you have an isotonic solution, that means two or more solution, they have exactly same osmotic pressure. They are called as isotonic solution. At this case, what will happen? C1 R2 is equal to C2 R2, or C1 is equal to C2, because T will get cancelled. Right, everybody? Very good. Finally, the last bit of the chapter, that is Van 't Hoff factor. Everybody, what is Van 't Hoff factor? To know the extent of association or dissociation of solutes in solution. So whenever you put solute, what will happen? Remember that interaction. So how much of A and B interaction happened? How much of A and B they associated? How much of A and B they dissociated? They moved away from each other. That is given by your Van 't Hoff factor. Okay, that is given by your Van 't Hoff factor. I is equal to normal molar mass divided by observed molar mass. I can be written as observed colligative property divided by normal colligative property. I can be written as actual number of particles divided by number of particles for ionization. Okay. All right. Now let us understand degree of dissociation and Van 't Hoff factor. Okay. For dissociation, everybody. So suppose that you have a reaction that AN forms N of A. Okay. So at time is equal to 0, this is happening. Okay, this is happening. Now suppose at time is equal to t. Yes, at time is equal to t. Let's say that 1 minus x of this reactant and n multiplied with x of this product has happened. How do I write I? We know that I is what? We have just see. Normal molar mass or observed colligative property. Observe normal molar mass, right? So 1 minus x, that means this plus product side. Yes. Now, what do we know? At t is equal to 0, this was 1 and this was 0, right? At time 0, the reactant was 1 and this was 0. So I can write here 1 plus 0. Or I can also write I is equal to 1 plus n minus 1 multiplied with x, right? I can write it like this. Yes, everybody? Yes? Yes, everyone? Very good. Now to understand what is N, what is this N, guys? What is this N? Suppose you have KCl. Now KCl forms K plus Cl minus. Here I will write N is equal to 2. That is the number of ions. Okay? That is the number of ions, everybody. Got it? Now similarly for association, if we do. Okay, for association. Suppose you have the reaction N of A. It forms AN. Yes. All right. Now, let's say that I want to divide it by N. Okay. Just in case. I want to divide it by N. Then can I write it as A? It forms 1 by N multiplied with AN. If I divide it by N, both the sides, I can do that. Yes, I can do that. So at time is equal to T. At time is equal to T, I will have 1 minus x of this and I will have x divided by n of this, right? So that means my I is going to be equal to 1 minus x plus x divided by n. Alright, everyone? Clear? Yes? Okay. Now, because we have introduced the colligative properties, we also have to understand that the moment we have introduced Van 't Hoff factor, what happens is, the moment we have introduced Van 't Hoff factor, the colligative properties change and you have to multiply Van 't Hoff factor with each and every colligative property. Okay? Alright. So delta TF becomes I multiplied with KFN, delta TB becomes I multiplied with KBN, pi V is equal to I multiplied with nRT, P naught minus P divided by P is equal to I multiplied with N2 divided by N1 plus I multiplied with N2, everybody. Got it? With this note, our solution chapter is over, guys. Solution chapter is over, everybody. Now let's solve some PYQs. Shall we solve some PYQs, everybody? No, let's solve the PYQs, then I'll give you a 10 minutes break. Let's solve PYQs, then I'll give you 10 minutes break, because after that even I want to go to the washroom and maybe, you know, drink a little water and everything. Okay? Yes, let us solve some PYQs. Chalo guys. So the first question, everyone, is define the term that is molality. Will you all be able to do it? Will you all be able to do it? What is molality, guys? Molality is defined as number of moles of solute divided by mass of solvent in kg. Am I right? This is your molality. Next question is define molarity, everybody. See, such easy questions are coming in your paper. Such easy questions. Yes. Now what is molarity, everybody? How do we define molarity? How do you define molarity? Very good. Is there anybody who is telling me the answer? Anybody who is telling me the answer? Very good. Absolutely. What is it? Moles of solute? Or no? Same, just in grams. 1 liter solution. Moles of solute divided by volume. Yes. Moles of solute divided by volume. Divided by volume of solution. Very good. Okay. Now here is a question, guys. The question says that a solution of glucose, molar mass of glucose is given to you 180 gram per mole. In water is labeled as 10% by mass. What would be the molality and molarity of the solution? Density is also given to you. Density is also given to you. So how do we solve it? Chalo. Mass of solute. See, 10% by mass, that means mass of solute. Mass of solute is equal to 10 gram, and this is going to be our component 2. Okay? Mass of solvent. Mass of solvent is going to be what? Suppose 10%, it is given 10%, that means 100 minus 10 is going to be 90 gram. 100 minus 10 is going to be 90 gram. So let's write here 90 gram, that will be equal to W1. Okay? Now what is the molar mass of the solute? See, molar mass is also given to you, that is M2 is equal to 180. Okay? Yes. Density is also given to you. Density is equal to 1.2 gram per milliliter. Am I right? Yes. So now how do you calculate molality? You will calculate molality as molality is equal to W2 multiplied with 1000 divided by M2 multiplied with W1. All you have to do is put the values. W2 is 10, 10 multiplied with 1000 divided by M2. M2 is how much? 90 multiplied with, M2 is 180, M2 is 180 multiplied with 90. Calculate this and tell me what is it. What is the answer? Calculate and tell me. Okay, chalo, you calculate this. After this, now we have to find out. Now we know density is given to you. So you want to find out the volume. Okay. So volume of solution, how do you calculate, guys? Volume of solution will be calculated as mass divided by density, isn't it? Mass divided by density. Now mass, we know that it is going to be 100 gram. Divided by density is 1.2, right? So now if I want to calculate molarity, capital M is equal to W2 multiplied with 1000 divided by M2 multiplied with volume. Can I write this? I can write this. Yes. So from here, W2 is given to us as 10. 10 multiplied with 1000 divided by M2 is 180 multiplied with 100 divided by 1.2. Now calculate this and tell me what is the answer. That will be your molarity and molality. So can you calculate this, everybody? Is this easy peasy biryani tasty? This is easy peasy biryani tasty, everybody? Yes? This is the kind of question that you will be getting in the exam paper. Okay? These are the kind of question that you will be getting. Chalo. Gas A is more soluble in water than gas B at the same temperature. which one of the two gases will have the higher value of KH? That is Henry's constant and why? And why? Now, what do we know? As per Henry's law, we know that the solubility of the gas is inversely proportional to Henry's law constant, right? Solubility of the gas is inversely proportional to the Henry's law constant. So, gas A is more soluble in water than gas B at the same temperature. So, gas B will have higher value, right? Gas B will have higher value. So, the gas B will have higher value. Gas B will have higher value. Yes, KH depends on the nature of gas, ray, not solution. KH depends on nature of gas, bacha, not solution. Now, explain the following. Henry's law about dissolution of gas in liquid. Can you do this? Henry's law, what does it say? It says that the partial pressure of the gas in vapor phase P is proportional to the mole fraction of the gas. So that means P is equal to KH. P is equal to KH multiplied with X, and KH here is the, KH is the Henry's law constant, right? And we all know that different gases have different KH values, but at the same temperature. Are we clear, guys? Yes, we are. Next question is, the partial pressure of ethane over a saturated solution containing 6.56 into 10 to the power minus 2 gram of ethane, then what will be the partial pressure? Yes. What will be the partial pressure, everybody? How do we calculate it? So we all know that molarity is also equal to KH multiplied with P. Now in this case, what is it given? It is given that pressure is 6.56, isn't it? Pressure is 6.56 into 10 to the power 2, 10 to the power minus 2, right? Yes, everybody? Yes, guys? Yes, everyone? So what will be the partial pressure? That is all that you have to find out. That is all that you have to find out, everybody. But wait a second. This question looks a little half done. No, this question is half done, guys. There is no. This question is half done, guys. Do not do this question. Do not do this question. I haven't noticed this question is half done. Yes, information is missing here. Information is missing here. I will have to know, Seema ma'am, that information is missing in the question. Yes. Mass will have to be given. Yes, mass will have to be given. Yes, bacha. You are right. No, this is wrong. This is wrong. Truly, it is wrong. Next question, let's see. If N2 gas is bubbled through water at 293 Kelvin, how many millimoles of nitrogen gas would dissolve in 1 liter of water? Assume that nitrogen exerts a partial pressure of 0.987 bar, given that Henry's law constant for nitrogen at 293 is 76.48 kilobar. Okay? Yeah, you are right. Yes, Sabarish, absolutely. So now as per Henry's law, we also know that pressure of nitrogen, P of nitrogen is equal to KH multiplied with chi of N2, right? Yes, everybody? Yes, everybody? Right, guys? Right, guys? This is clear? Right? Very good. Now, from here, we see that we have to find out chi of N2. If the N2 is how many millimoles of N2. Okay, so XN2 is equal to, how do we write it? PN2 divided by KH. Now, PN2, is it given to us? Yes, partial pressure is given to us. That means 0.987 divided by, what do we have, 76.48 kilobar. So we can write it as 76480 bar. Calculate this, guys. How much will you get? Calculate this. How much will you get? Calculate this. How much will you get? And tell me the answer. Okay? Once you're done with this, now we want to figure out millimoles, right? So if n moles of N2, this is the question, right? If n moles of N2 are present in let's say 1 liter. 1 liter is only given to in the question, right? That means, now what is the molar mass of N2, guys? 55.55 moles, isn't it? 55.55 moles, am I right, everybody? Yes? Yes. So that means that chi N2 is equal to N divided by 1 plus 55.55 is equal to N divided by 56.55 of water, or 55.55 of water. Am I right, everybody? Yes, 55.55, correct? Acha, that value is 1.29. Okay, 1.29 into 10 to the power minus 5. Okay, all right. Now after this, what do we do? After this, what do we do? So that means that n divided by 55.55 is equal to 1.29 into 10 to the power minus 5. Yes, that means that n is equal to 1.29 into 10 to the power minus 5 multiplied with 55.55 moles, everybody. Calculate this, and whatever moles you get, just convert that into millimoles. Just convert that into millimoles. So will you all be able to do this? Yes, Muhil has also solved. Very good. Trichi, hi FCL Trichi bacha. How are you doing? You're very late to the class. But anyways, this done. Shall we go to the next question? I think calculation part you can do it. Okay, next is, give reasons for the following. Aquatic species are more comfortable in cold water than warm water. Don't we know? As you increase the temperature, solubility decreases. Solubility decreases. That is why. Yes, very good. Okay. Now, Sabarish, what are you? Sabarish, bacha, come on, yeah. Class 11 mein you have studied, no? Also, you don't have to do this. Let's suppose that whatever value you get, you will get it in 10 to the power minus 3 moles, okay? You will get it in 10 to the power minus 3 moles. So just write whatever you get, 0 point something 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 millimoles. Just write that, okay? Just write that. That is enough. That is more than enough. Okay? Alright. Next question, everybody. At higher altitudes, people suffer from anoxia resulting in inability to think. At higher altitude, the partial pressure of oxygen is less than at the ground level. So what happens? As a result, there is low concentration of oxygen in the blood and tissues of the people living at high altitudes, and that's why they feel weak and they are unable to think properly. Right, everybody? Yes, yes, yes. Very good. Chalo. Next question is, define Raoult's law. Will you all be able to do it? Define Raoult's law, everybody. I think you will all be able to do it. Take this as a homework and you can all solve it. Okay? You can all solve it. Oh, we are done, guys. We are done with our solutions chapter completely. Completely we are done. Completely we are done. Yes, everybody? Great. Shall we take a 10 minutes break? I need to go to the washroom. Need to go to the washroom. We will take a 10 minutes break. Okay? We'll take a 10 minutes break. After that, we will come back. Okay? Then we will solve chemical kinetics. After that, electrochemistry. And then tada bye-bye. Okay? But now, not tada bye-bye. Yes, I have just finished solution chapter. After this, we will be doing chemical kinetics, guys. So take a break for 10-15 minutes. 10 minutes. I'll give you 10 minutes ka break. Okay? Not more than that, guys. 10 minutes break, everybody. Starting it. Okay? Yeah. 10 minutes break. Chalo. See you in 10 minutes, guys. ठीक है? See you in 10 minutes. Bye. All right, hello guys, we are back. Hello guys, we are back. Quickly go and call up your friends because now we are starting with full Josh chemical kinetics and electrochemistry. This will be done in the next 2 hours. In the next 2 hours, we will be completing it. And Arjun, hi bacha, yes. All right, hello guys, we are back. Arjun, I have just replied. Yes, you must complete. Yes, today was the fastest, ma'am. That's so cute here. That's so cute. Alright guys, are we ready everybody? Yes, let us start. Yes, without much further ado. Because now we have to do, these 2 chapters are a little tough. Yeah. Break goes faster than the class time. What to do? Seriously. Yeah. Okay, so what do we mean by this chapter, chemical kinetics? What actually do we study in chemical kinetics? You know, we studied thermodynamics in class 11, right? And when we studied thermodynamics, we got to know that yes, that decides the feasibility of the reaction. Is the reaction going to happen or not? That is something that thermodynamics tells us. But, why are we reading about chemical kinetics then? My dear students, we are reading about chemical kinetics here. That's because, wait a second. I need white color. Where is white color? Here, found it. Huh. So why are we reading about chemical kinetics? Because this chemical kinetics, this chapter, it can tell us about rate. It can tell us about velocity, how fast is the reaction happening. Basically, it can tell us about the speed of a reaction. And my dear students, tell me what is speed? Speed. How do you talk about speed? How do you tell what is speed? Speed is what, guys? Distance divided by time. Distance divided by time is speed. Exactly. So when we come across chemical kinetics, the first thing is a definition here. So how do you define this chemical kinetics? We define it as, my dear student, the first thing that we define it as is feasibility of the reaction. Yes, from chemical kinetics, we do get to know the feasibility of reaction. Yes, but this feasibility of the reaction is very well told by thermodynamics, everybody, right? In thermodynamics, we get to know this a little more because in thermodynamics, do you remember we studied that delta G, if it is greater than 0, if delta G is equal to 0, then what will happen? This will be equilibrium. Yes, this will be equilibrium. Right? Then we studied in thermodynamics that what will happen if delta G is lesser than 0, isn't it? In this particular chapter, we talk about the speed of reaction the most, okay? What do we learn about from this chapter? Speed of reaction. And there is another chapter which also tells us about the extent to which the reaction is happening. Till what extent? Is the reaction going to get completed? Is it not going to be completed? All of these we get to know from where guys? Where? Equilibrium. Chemical equilibrium, ionic equilibrium. Remember that extent to which the reaction will happen. Till what extent? Is the reaction going to get completed? Is it going to be half done? That we will get to know from the chemical equilibrium chapter. But we don't have to talk about that at all now. Shall we move ahead then? Okay? Chalo. Now, moving forward, everybody, what is average speed and instantaneous speed? Please pay attention because there was a previous year question that actually spoke about it, okay? That actually asked you what is the difference between average speed and instantaneous speed, everyone. So, what is your average speed, guys? What is your average speed, everybody? Your average speed, my dear students, is total distance traveled. Yes, it is total distance traveled divided by total time taken. Right? Now, the question is, what is instantaneous speed? What is instantaneous speed, guys? What is instantaneous speed then? What is instantaneous speed? Instantaneous speed is, my dear student, dx divided by dt. That is your instantaneous speed. Okay? Alright, everybody. Now we come across rate of a chemical reaction. From this graph, you see that time is taken in the y-axis and concentration is taken in the x-axis. Time is taken in the x-axis and concentration is taken in the y-axis. And you see that the red color part, it shows the product formation, and the blue color part shows the reagent formation. So from here, we can calculate the rate of a reaction. Okay, we can calculate what rate of a reaction. And what is the formula that we are going to use for rate of a reaction? We will use change in amount of chemical species, okay? Change in amount of chemical species divided by, what do we do? Divided by time taken. Divided by time taken. That is your rate of reaction, everybody, okay? That is your rate of reaction. Now, if we want to talk about what is the average rate of reaction, what is the average rate of reaction going to be? I mean, obviously, it is very easy. Reactants are going to form products. Am I right? Yes. Now, we know that the average rate can be written as minus delta R divided by delta T. Now, why have I mentioned minus? Because over the time, the reactants are decreasing. And why have I mentioned a square bracket? The square bracket here depicts the concentration. Whenever we are writing the square bracket, that means that by this we mean concentration. Okay? All right. Now this average rate can also be written as delta P divided by delta T. Here I have not mentioned any minus sign. Why? Because there is formation of product that is happening. Yes, products are being formed here. So we are writing delta P divided by delta T. Cool. Now guys, if we want to talk about instantaneous rate of reaction, how do we write this? We will write it as RINST, that means instantaneous. This time we are going to write minus D capital R divided by dt. Once again, do you notice that I have mentioned minus? Why? Because reactants are going to get reduced, okay? Reactants are going to get reduced over the time. For example, if I have hydrochloric acid and sodium hydroxide, over the time you will see that hydrochloric acid and sodium hydroxide, they are disappearing. What are they doing? They are disappearing. After their disappearance, there is formation of sodium chloride and water. So these two products, they are appearing, and these two products, they are disappearing. Isn't it, everybody? Yes, guys. Very good. Now here, R instantaneous can also be written as dP divided by dt. Yes, guys. Yes, absolutely yes. Absolutely yes. Right? And imagine that generally, okay, let's take a general reaction, and let's suppose that our general reaction is A plus B forms C plus D. For this reaction, our instantaneous rate, that is instantaneous rate, I can write it as rate instantaneous, will be equal to minus dA divided by dt is equal to minus dB divided by dt is equal to dC divided by dt is equal to d divided by dt. But is that all that we are going to write? No. We also write the coefficient, this coefficients. This also we will write here. Here you will write A, B, C and D. Okay, this is what you write. And once again, everybody, as I told you yesterday, that these two are your rate of disappearance. Okay, these are rate of disappearance of the reactants, and these two are, my dear students, rate of appearance. Okay, these are rate of appearance. Am I right, everybody? Is this clear to you till here? Is this clear to you here? Okay. Now, one thing let me tell you, everybody, that divide by coefficient when you are finding the rate of the reaction. Once again, listen to me very carefully. If you are asked to find the rate of the reaction, then yes, divided by the coefficient. But if you want to find the rate of a particular species, then you do not have to divide it by the coefficient. Got it, everybody? Is this clear, guys? Is this clear to you all, everyone? है ना? ठीक है. Okay. Now let us talk about the rate of reaction and their units. So everybody check it out. How are we writing? R is equal to, rate is equal to minus dr divided by dt. Isn't that we are writing? Which is equal to, we are writing dp divided by dt. That means that on the top, in the numerator, we're talking about concentration, and at the denominator, we're talking about time. Now, how do you write concentration? Concentration usually is written as mole to the mole and s to the power minus 1. No, liter, sorry. Liter, not s. Huh. Liter, okay. Liter to the power minus 1 divided by time is second. That means that it will be mole liter to the power minus 1, s to the power minus 1. Now, this is only for liquids. This is only for liquids. What if we have a gas? What if we have a gas? At that point, you will take ATM s to the power minus 1. This is going to be the unit. Is this clear, guys? Till here, everything is clear, everybody? Till here, are we all clear, everyone? Yes, very good, everybody. Very good. Are we clear, guys? Till here, any doubt? Till here, any doubt? Alan, very good. Simi, Nipun, everybody. Sushrita, Sunena, are you guys understanding? Are you guys understanding? Yes? Okay. Chalo. Now let us talk about the rate of reaction expression. Okay. So let's say that suppose you have a reaction where the stoichiometric coefficient is equal to 1. Okay. Stoichiometric coefficient is equal to 1. Suppose you have a reaction where stoichiometric coefficient is equal to 1. For example, let us take the example of everybody, mercury, okay, Hg plus Cl2 in gaseous form is forming HgCl2. Do you see that everywhere the coefficient is 1, 1 and 1? Do you notice, everybody, that everywhere the stoichiometric coefficient is 1? Now, in this case, what is going to be my rate of reaction? My rate of reaction is going to be minus delta here, concentration of Hg, divided by delta T. This will be equal to minus delta Cl2. Now, actually, for this, we will only write Cl2, delta T, because here we are supposed to take pressure because it's in gaseous phase, right? This will be equal to delta HgCl2 divided by delta T. Am I right? Am I right everywhere? Very good. Now suppose I have another reaction, okay, another second case where the stoichiometric coefficient, my dear students, is not equal to 1. Okay, stoichiometric coefficient is not equal to 1. At this point, suppose you have a reaction which is N2 plus 3H2 forms 2NH3. If this is the case, then how do you write the rate of reaction, guys? Rate will be equal to minus delta N2 divided by delta T. Yes, this will be equal to minus delta H2 divided by delta T. But here you will have to divide it by the stoichiometric coefficient, right? Yes, this will be equal to delta NH3 divided by 2 multiplied with delta T. Am I right, everybody? Yes, am I right, guys? Am I right, everybody? This is going to be your rate of reaction expression. Yes. Now, let us come to the point that what are the factors that affect the rate of reaction? How can you tell that if the rate of reaction is it going to be faster, is it going to be slower? How can you tell, my dear students? Well, there are 4 major factors. Number 1 is, of course, temperature. Yes. Number 2 is your concentration of reactant. Okay. Concentration of reactant. All right, everybody. Number 3 is catalyst. Are there catalysts? They are used. Okay. All right. And finally, you have nature and state of reaction. है ना? Nature and state of reaction. So these are the ones that affect the rate of reaction. All right, everybody. Yes. Okay. Jessica बच्चा, why are you not able to understand? आपने कभी पढ़ा नहीं है ये चैप्टर? हाँ, अभी आपका बोर्ड्स है ना 3 दिन में. 27 को आपका बोर्ड्स है ना, आपको नहीं पता? क्या करते हैं इस चैप्टर में? हम रेट ऑफ रिएक्शन निकालते हैं, है ना? इस चैप्टर में हमें पता होता है कि रेट ऑफ रिएक्शन निकालना है कि नहीं निकालना है. Vitesh, yes, we know that ideally if it was, but see, the state is not mentioned. The state is not mentioned. So I took the liberty of writing the concentration. If the state is mentioned, then you cannot do this. Then you have to take the pressure. Got it, Vitesh? That's why I took the liberty here because state was not mentioned. I did not mention the state here. That's it. Okay? Huh. So chalo guys, moving on everybody. This much is understood guys? This much is understood? Yes? Suppose if I take solid iron rod and then if I add some hydrochloric acid in it, okay? Suppose I take some solid iron rod and if I add some hydrochloric acid to it, then what will happen to the reaction guys? What will happen to the reaction? The reaction, I guess all of you will agree with me that yes ma'am, this is going to be slow. This is going to be slow. But instead of taking an iron rod, if I take iron filling, that means powdered iron, and then if I mix it with hydrochloric acid, then will you all agree with me that the reaction is going to be very fast? Then the reaction is going to be very fast? Absolutely. Absolutely, everybody. So the nature of reactants when we write, that means that here we can say, everybody, I want a little nicer color of green. Yeah, this is nice. This is nice here. So now when we do this, everybody, yes, now when we do this, very good, very good. This is going to be fast, isn't it, Trisha? Very good, yes. So that means here I can say that the physical state of the reactant will matter. The physical state of the reactant will matter. Yes. What do we notice? We notice that if I take solid phase of reactants, the solid phase of reactant will give us a slow reaction. Will give us a slow reaction. But if I take a gaseous phase of reactants, that means that I will be getting a fast reaction, isn't it? Isn't it? I will be getting a fast reaction, everybody. Yes. So obviously from here I can also say that state of reactants. What state the reactants in, that will also matter to us. Like I just told you. Like I just told you that if it is solid, slow. If it is gas, it is definitely going to be faster, isn't it? So state of reactant, the nature of the reactant, it does matter to us, everybody. It does matter to us. Now let us talk about the concentration of reactants, as in what will happen if we increase the concentration of the reactant. Bro, obviously the rate will increase, no? Because I have increased the concentration, that means that more reactant are available to form product. So if I decrease the concentration, it will obviously decrease. So that means that I can clearly write here, everybody, that rate increases, okay? Rate increases with an increase in concentration, and it decreases with a decrease in concentration. Crystal clear? Very easy, very peasy, everybody. Yes, this is also easy peasy. Correct? Correct, guys? Very good. Okay. Once we are done with this, now we come across the actual picture of this chapter. That is, my dear students, yes, that is, my dear students, your differential rate law. All right, everybody. So first of all, let us take a general reaction. Let us suppose that we have alpha A plus beta B forms gamma C plus delta D. Okay, let's suppose that we have a reaction like this. Okay, so how can I write the rate now? Rate will be proportional to, my dear students, to what? A raised to the power x and B raised to the power y, let's say. Okay. Now you're going to ask me, ma'am, what is x and y? You're going to ask me, ma'am, what is x and y? So I'm going to write it down here that x and y are, okay, what are x and y, guys? X and y are determined experimentally, okay? X and Y are determined experimentally. Okay, experimentally. And sometimes what happens, this X or and Y, sometimes they may be equal to the stoichiometric coefficient, sometimes they are not. So we can write it here with a star mark that X and Y, okay, X and Y may or may not be, may not be equal to the stoichiometric coefficient. Okay, all right everybody. Yes, this is an important note. Okay, this is an important note. All right everybody, cool. Now everyone, so since I have, everybody check it out, since we have a proportionality sign here, that means we want to remove it. And how do we remove it? We are going to write that rate is equal to K multiplied with A to the power X and B to the power Y, everybody. This K, my dear student, what is it? This is your rate constant, everybody. Yes, and that means that what is rate, guys? Rate can be written as minus D multiplied, minus D of R divided by dt can be written as K A to the power X B to the power Y. Clear hai? Clear hai, everybody? Yes, everyone? Yes, yes, yes or no, guys? Yes or no, guys? Do you understand this? Do you understand this, everybody? Great. Okay. All right. Yes. Okay. Now let us talk about order of reaction. What is order of reaction? So you must have heard, right? First order reaction, zero order reaction, pseudo order reaction, isn't it? Yes. We have spoken about this. Very good. We have. So order of reaction is given to us by, who gives us the order of reaction? The sum of the powers of the concentration of the reactants in the rate law expression will be called as order of the chemical reaction. Okay, all right, so check it out. We can write it down here that sum of powers of the concentration of the reactants in the rate law expression is called the order of that chemical reaction. Okay, is called as order of that chemical reaction. Now read the definition, everybody. Do you understand? Now let me give you some examples. I think you will understand better. So imagine that we have X plus Y, only X plus Y. Yes, this X plus Y, this is going to tell you the order of reaction. This is going to tell you the order of reaction. So imagine if we have X plus Y is equal to 0. That means that this is a zero order reaction, right? That means that this is a zero order reaction. What if we have X plus Y is equal to 1? That means that this is going to be a first order reaction. This is going to be a first order reaction. All right. Now if X plus Y is equal to 2, that means it is going to be a second order reaction. Am I clear, everybody? So this is basically how it goes on. Okay. This is basically how you go ahead and you can write down, and that is when we study about the nth order of reaction as well. Okay. All right, everybody. This is clear, guys. This is all clear to you all. Yes, okay. Now moving on, let us talk about the zero order reaction. For example, everybody, let us take, for example, let's say that we have hydrogen plus chlorine here, okay? And here, let's say that light is falling. So what will we get? We will get HCl, let's say. Okay. Here, what happens to the rate is, everybody, rate will be given to you as a K multiplied with H2 to the power 0. And you will have Cl2 to the power 0. Okay. If that is the case, my dear students, then what is going to be the rate here? Here, do you see that X is 0, Y is 0? That means that the concentration of the reactants are not changing with time. But how did I come across that? Because see, rate is equal to K, I can write. Yes. What is K? K is rate constant. If that is the case, then I can definitely write here that the concentration of reactants, okay, the concentration of reactants are not changing with time, okay, they are not changing with time at all, okay, they are not changing with time at all. Everybody got it? Yes, got it? Yes, this is a zero order reaction, and you have to note whenever in the question they are writing that the concentration of the reactants are not changing with time, just write that this is a zero order reaction. You just have to write that this is a zero order reaction. Cool? Okay, guys. Quickly moving on to the first order reaction now. Imagine that we have a, let's suppose that we have a reaction N2O5 and this forms, let's say 2NO2 plus half O2. Okay. Now here rate becomes, here rate is equal to given as K N2O5 to the power 1. So here what can we write, guys? We can write, my dear students, check it out. Rate is equal to K multiplied with A to the power 1 and B to the power 0. Or it can also be, maybe there is a possibility that you have a reaction where A is to the power 0 and B is to the power 1. That is also possible. Then also you will have a first order reaction, isn't it? Then also you will have a first order reaction. Now let us talk about second order reaction, guys. For second order reaction, suppose you have 2HI which forms H2 plus I2 on decomposition. So here rate is basically KHI raised to the power 2. Now in this case, everybody, in this case, guys, please have a look. Rate can be, okay, rate can be K multiplied with A to the power 2, right? It is a possibility. Or it can be K multiplied with A to the power 1 and B to the power 1. Or it can be K B to the power raised to B raised to the power 2. That is also a possibility. Am I right? That is also a possibility, isn't it? If A to the power 0, then we don't write it. If B is raised to the power 0, then we don't write it. So we are writing this, okay? Basically, what I mean to say is, who is asking me that, ma'am, why only A? Alan, why B? We only have one reactant. No, but listen. Either it is A to the power 2 and B to the power 0, or B raised to the power 2 and A raised to the power 0. Got it? Instead of writing A raised to the power 0, I just wrote B raised to the power 2. Got it? Yes? Yes, understood? Understood? Yes? Okay. Very good. Now the question that comes in our mind is, but ma'am, can the order of reaction be fractional also? You know what? If I tell you the answer, yes, it can be. It can be fractional. Shall I give you an example? See, if you take CHCl3 plus Cl2 and it will form CCl4 plus HCl, what is going to be the rate here? Again, these are all experimentally observed values, okay? So here you will see that K multiplied with CHCl3 to the power 1 and Cl2 raised to the power half. So yes, the order of reaction can be fractional as well. The order of reaction can be fractional as well, okay? Now guys, let us talk about units of K. Once again, everybody, you might be asked about units, so please pay attention. So let us suppose that once again we have a general reaction which is alpha A plus beta B forms gamma C plus delta D. Suppose we have a reaction like this, okay? Now can you all tell me what is rate going to be? Rate is equal to K multiplied with A raised to the power X, and we know that B raised to the power Y, right? So here K is equal to, guys, K can be written as rate divided by A raised to the power X and B raised to the power Y. This is equal to concentration, yes, divided by time. Rate is concentration divided by time. And what is A and B? A and B are concentration, so concentration raised to the power X plus Y. That means that now if we have a zero order reaction, guys, check it out. If we have a zero order reaction, for a zero order reaction, the unit of K is going to be, concentration divided by time, divided by, see, x plus y is what? 0. X plus y is what? 0. So anything concentration raised to the power 0, that means that this is what? Equal to 1. This is equal to 1. And if I have something that is equal to 1 in the denominator, that means that I can write it as mole liter to the power minus 1 s to the power minus 1, and this is going to be my unit. Tell me if this is easy peasy biryani tasty, everybody, till now. Easy peasy biryani tasty, everybody. Yes or no, guys? Yes or no, everybody? Yes? Very good. Similarly, moving on, everybody, let us talk about the first order reaction. Okay, for first order reaction, everybody, if you check it out, here you have first order reaction. For a first order reaction, everybody, unit of K is equal to, sorry guys, apologies for my bad handwriting, unit of K is equal to, everyone, concentration divided by time, obviously, divided by concentration, and this time it is raised to the power 1. So that means I can write it as concentration divided by time is equal to, not equal to, multiplied with 1 divided by concentration. Can I do this? This whole term only, I have separated it and written it. So that means concentration cancelled. Only 1 divided by time is left. That means what can I write it as? S to the power minus 1. And that is the unit for first order reaction, everybody. That is the unit for first order reaction, everyone. Getting my point, everybody? Are you guys getting it? Yes, very good. Okay. Now moving on, let us talk about the second order reaction, everyone. Here I am going to write the second order reaction, everybody. Check it out, guys. Okay. Yes, here you have the second order reaction. Unit of K for second order. See, I am actually deriving it for you and I am letting you know. Okay. For second order, it is going to be concentration divided by time divided by concentration. But this time it is raised to the power 2. So that means one concentration cancels. So you can write it as mole to the power minus 1 L S to the power minus 1. Am I right, everybody? Can you do this? Yes, can you do this? Very good. Yes, second order is not for board. Acha chalo, theek hai. Just the unit I am telling you. Just the unit, that's it. Nothing else, okay? I've just told you the unit. Chalo. Now let us talk about molecularity of a reaction. Suppose you have an elementary reaction. Okay. Suppose you have an elementary reaction. Chalo, let me write that down. I think then you will be able to understand this a little bit easily. Okay. Guys, this is not a very huge chapter. Okay. After molecularity and order of reaction. 1 second, everybody. Check it out. After molecularity, then you have integrated rate equation. After that, half-life. After that, pseudo-order reaction, temperature dependence, Arrhenius, collision theory, probability, catalyst dependence. And that's it. Done. Not too many topics, guys. Okay. Not too many topics. Chalo, guys. Moving on quickly. Just stay back. Okay. Just stay back. It's already about to be 4. I think by 4:30 we will be done with this session. Okay. By 4:30 we will be done with the this chapter. Okay. So suppose you have an elementary reaction. Okay. You have an elementary reaction. And this elementary reaction, my dear student, is suppose you have NH4NO2. It forms N2 plus 2H2O. Suppose. Okay. Yes. Now here, what can I write for molecularity of reaction? Somebody has already written it. Yes, Monish, very good, very good. Yes, number of reacting species. It can be atoms, ions or molecules which are taking part in the elementary reaction, which must collide simultaneously in order to bring about a chemical reaction. That is your molecularity of reaction. Okay, that is your molecularity of a reaction. For example, now let's check it out, everybody. See. So here I'm going to write this down, okay? I'm going to write this down, that number of reacting species. Number of reacting species, and it can be atoms, ions, or it can be molecules, okay? Or it can be molecules taking part in an elementary reaction, okay? Taking part in an elementary reaction which must collide simultaneously in order to bring about a chemical reaction. Okay? Alright guys, this is the answer. Everybody, guys, are you understanding or not understanding? Let me know. Very good, Govardhan. Very good, everybody. Yes, yes, yes. Yes, guys, understanding? Yes, okay, very good. ठीक. Now let's say that we have a unimolecular, okay? What is unimolecular, guys? What is unimolecular? I'll also show you. See. Let's suppose that we have a unimolecular reaction. How is it unimolecular, everybody? I'm going to write down the example, and then you are going to tell me that how is it unimolecular, how is it bimolecular, how is it trimolecular. Okay? NH4 NO2 forms N2 plus 2H2. Okay? Next, let's say that I have a bimolecular reaction. Okay? Bimolecular bole to, suppose 2HI forms H2 plus I2. Okay? Then let's say that I have trimolecular. One second. Trimolecular or termolecular. Okay, this is also called as trimolecular or trimolecular. Have a look and then tell me how is it termolecular. See, you have 2NO plus O2 forms 2NO2. Now look at the examples and tell me, do you understand how it is bimolecular, how it is termolecular, how it is unimolecular? Do you guys understand this, everybody? Yes? Very good. See, unimolecular, only one molecule is decomposing to form two molecules. Here you have two molecules. The stoichiometric coefficient here is 2. Hence, it is bimolecular. Here you have two molecules plus another one molecule of oxygen. That is why it is termolecular. Got it, everybody? This was easy peasy, right? This was easy peasy. Very good. Okay. Now we know that the reactions are not always very easy peasy biryani tasty, right? The reactions are not always very easy. The reaction do not occur in just single steps all the time. There are many reactions which are complex in nature and they occur in multiple steps, right? They occur in multiple steps. For example, suppose you have a reaction where KClO3 plus iron sulfate plus sulfuric acid is reacting and it is forming potassium chloride and everything. Yes. At that point of time, the reaction, actually, you know what? Let me draw it and show it to you. Okay? Let me draw it and show it to you. So suppose you have a complex reaction. Suppose you have a complex reaction and your reaction is, everybody, let's say that KClO3 plus 6FeSO4 plus 3H2SO4. This forms here KCl plus this forms here 3Fe2SO4 3 plus 3H2O. If this is what it forms, does it not look like this is a 10th order reaction? Does it not look like it's a 10th order reaction, everybody? Huh? It does look like it's a 10th order reaction, isn't it? Right? This reaction looks like it is a 10th order reaction. But actually no. Actually it is a second order reaction. Because the overall step of the reaction, it is controlled by the slowest step in the reaction, and that becomes the rate determining step, everybody. Do you guys understand? Yes, Vandana, super amazing, everybody. This is actually a second order reaction where you have the rate determining step that will take care of the order of the reaction. Got it? Yes. Now, if we want to differentiate between molecularity and order of reaction, will you guys be able to do it? Will you guys be able to do it? Chalo, let's write this down. This can be determined by looking at elementary reaction, right? By elementary reaction. From elementary reaction, you can calculate this molecularity. Order of reaction, my dear students, order of reaction will always be experimentally calculated or experimentally determined. Experimentally calculated. Can I write that? Can I write that, everybody? Yes. What is molecularity, guys? Sorry, molecularity here, everybody, is molecularity is what? It is equal to the sum of stoichiometric coefficient, right? Equal to sum of stoichiometric coefficient. All right. Yes. It is always, molecularity can be unimolecular, bimolecular, trimolecular, termolecular. That means a whole number. It is always a whole number, guys. It is always a whole number. All right. Molecularity is only applicable for elementary reaction. Okay. Here I am writing it down. Applicable for elementary reaction. Alright, guys, here, okay. But here, if I write it down, see, here, this is experimentally calculated. Secondly, what can I write? Is this equal? No. Is this equal to the sum of stoichiometric coefficient? No. It is equal to sum of powers of concentration in rate law. Very good, Balaji, very good. Yes. Thirdly, what can I do? Order of reaction can be 0, 1, 2, 3, fraction, or it can be negative. Fraction, or it can be negative, isn't it? Yes. And finally, we can write that the order is applicable for elementary as well as complex reaction. So, applicable for elementary as well as complex reaction. So now I have written only 4 sets of differences, but you obviously can write even more. Okay? Alright, you can write even more. Chalo, guys. Now, molecularity and order of reaction. Let's take a look at some of the example. Yes. Yes. Alright, chalo. Now let us take a look at some of the examples, everybody. Suppose you have an example of 2H2O2, that is hydrogen peroxide. Yes. Here is I minus and there is alkaline medium, everybody. Let's say you have alkaline medium. Yes. What will it form? It will form water plus it will form oxygen, right? Now, do you think this is an elementary reaction or it is a complex reaction? Actually, it is a complex reaction, guys. It is a complex reaction. Okay? So, in this case, when we have a complex reaction, everybody, what can we write here? What can we write, guys? Here, everybody, chalo, let's check it out. Let's write down. So, the first step here is actually H2O2 plus I minus. Okay, they reacted. And what does it form? It forms H2O plus it forms IO minus. What do you think? This is the slow step or this is the, this is the faster step. Which one is this? This is a slow step. That means this is the rate determining step. Now, in the second part, what happens is you have IO minus plus H2O2 will react and then it will form H2O plus I minus plus O2. Now this is the fast reaction. Okay, this is the fast reaction. Okay, so here now what happens is the rate can be written as K multiplied with H2O2, and here we will write I minus, because these are the reactants, isn't it? These are the reactants. So this is going to be the rate, correct? This is going to be the rate. Similarly, we can take another example. Let us take another example, everybody. Let us take another example. Chalo, let us take another example. This time, let us take the example of 2NO plus O2 forms 2NO2. Okay. So here, again, let us write the reaction in two parts. Okay. Let us write the reaction in its parts. So here we will see that NO plus O2 forms NO3. And this, my dear student, is the fast reaction. Okay. But here, if I write the second part of the reaction, which is NO3 plus NO react, and what do they form? They form NO2. So this, my dear student, this is your slow rate determining step. Now, what is going to be my rate here, my dear students? My rate is going to be K multiplied with NO3 here, and here I will write NO, because this is my rate determining step, isn't it? Yes, very good. Very good. Absolutely. But tell me something. Can I also write it as K and then K dash? Okay. K dash. Here, can I write NO, and then can I write here O2, and then can I write here NO once again? Can I do this? I can do this. I can do this. Why did I do that? Chalo, let me show you here. Here is the rough work, everybody. Check it out. See, my K dash is going to be equal to NO3 divided by NO multiplied with O2. Am I right? That means that NO3 is equal to K dash NO multiplied with O2. Am I right? So exactly this is what I have put it here. Now, once I have done this, that means my rate is going to be equal to K double dash here. Let's write it K double dash, and then I can see that NO twice, so NO square. And then I can write here O2. This is going to be the rate, everybody. Do you guys understand now how to do this rate thing? Do you guys understand, everybody? Yes. Now, guys, let us quickly move on towards the integrated rate of equation, or the rate law that we know as. Yes, we know this name called rate law. Exactly. So let us take a look at this. Now here, what do we write? Integrated rate of equation. What is it? Integrate the differential rate equation. But all these differential equations that we had, we just have to integrate it. So chalo, let us write it here. Integrate the differential rate equation to give a relation between directly measured experimental data, that is concentration at different times and rate constant. That, my dear student, is your integrated rate law. That, my dear student, is your rate law basically. Okay? Now, let us do this. Let us find the integrated rate equation for zero order. Shall we, everybody? So, chalo. Zero order. For zero order, rate is equal to what? For zero order, rate is equal to minus dr divided by dt. Am I right? Yes. Which is basically equal to, we know that it is kr to the power 0. That means we can write it as k, just k, r to the power 0 is equal to 1. Anything that is equal to, anything that is raised to the power 0, it is going to be equal to 1, isn't it? Yes. It is going to be equal to 0. Yes. What is it? How order determined by complex reaction? How order is determined by complex reaction? If you have a complex reaction, then you have to write down the steps of the reaction. Find the slowest step. The slowest step is always the rate determining step. Okay? All right? Yes. Okay, guys. Now, suppose, so we have this, right? This is our rate. For a zero order reaction, this is the rate, isn't it? Very good. Now what do we have to do is we have to integrate it. You all know how to integrate it. So you have minus dr divided by dt is equal to, here see, kr, right? So all we can do is just write here r. Can we do this? Very good. Now if we integrate dr by dt, that means that this will become d concentration of r, and r here is, we know that it is kr naught, so minus k, because k is a constant always comes out of integration, and then here write dt. Am I right, everybody? Am I right, everybody? Yes, guys. Very good. Okay. Now here, see, if you write here r, this will be equal to, see, minus kt plus, there will be some constant. Integration, you know. You guys know what is integration? Yes. Now guys, let's suppose at time is equal to 0, we all know that concentration of r is going to be equal to r naught, initial concentration, right? Initial concentration. And r naught is equal to 0 plus some constant, that is what something that I can write here. How so? Chalo. How so? How did I write that? Let me explain this to you here. See, r is equal to minus kt plus r naught, I can write. Yes, because this is the zero order reaction. From here, y is equal to mx plus c. Does this make sense here, everybody? Yes. This equation looks like y is equal to mx plus c. What is c? C is your intercept. C is your intercept. Isn't it, everybody? Isn't it, everyone? No, bacha, you don't have to remember the derivation, but you have to learn the derivation to understand how we have arrived at this point. Okay? You don't have to you don't have to learn the derivation, but you need to know how we arrived at this part. Okay? Okay? Derivation you need to know. You should know, but you don't have to learn it. So 0 plus constant, that means that constant is equal to r naught. Right, everybody? Now that we have already figured out that y is equal to mx plus c, it looks like that graph. Okay, it looks like that graph. So everybody, if I draw the graph now, guys, if I draw the graph, everybody, okay? Chalo, guys, look at it. I'm gonna draw the graph here. Okay, here what do you have? Let's suppose we take concentration in the y-axis, and here we take time. Okay, this is going to be the graph. This is going to be the graph, and this part is called as your r naught. Okay, this part is called as the r naught. See, this is the intercept, this is the r naught. Yes, intercept is r naught. So we have figured that out. Okay, everybody? Yes. Now suppose we want to talk about the first order reaction, guys. Okay, let us talk about the first order reaction. Very good, Dexter. Very good. Absolutely very good. Yes. Yes. So now we have the first order reaction, guys. Okay. Now we have the first order reaction, everybody. So we have, once again, what is the rate for first order reaction? It is minus dr divided by dt. Yes. And that is equal to kr to the power 1. Okay. Not power 1. Basically, we are talking about the first order. So we are writing here 1. Okay. All right. Let's integrate this. So it will be dr divided by dt is equal to minus k dt. Am I right? Now if I take natural log on both the sides, I will be getting ln of r is equal to minus kt plus c. Can I do this? Can I do this, guys? Acha, no. One mistake. Sorry. Here, instead of dt, let us write, this is k r naught, k and dt. Acha, r1, r will come here. Okay, r will come here. Now if I take natural log, so it will be ln of r is equal to minus kt plus c, right? Now at time is equal to 0, everybody. At time is equal to 0, capital R is equal to r naught. This is our initial concentration. Am I right? Now if I take ln of r naught, okay, ln of r naught is equal to 0 plus c. That means that c is equal to ln of r naught. Am I right, everybody? Am I right, everybody? Yes, guys. Okay. Now moving on from here, everybody. Again, these are derivations that you don't have to learn, but you should know. How did you arrive at that part? That you should know. Okay. So from here, I can write ln of r is equal to minus kt plus ln r naught. ठीक है? Once again, if I equate this is equal to y is equal to mx plus c. If I equate this, guys, if I equate this, then what will I get? I will be getting ln of r, sorry, this will come this side, so minus ln r naught. Yes, this is equal to minus kt. Am I right? Yes. Now, can we apply the logarithm property? Can we apply the logarithm property, everybody? We can. So here what will it happen? ln of r divided by r naught. This is equal to minus of kt. If I convert this natural log to log base 10, then what will I get? I will be getting 2.303 log of log r divided by r naught, which is equal to minus kt. Am I right? Very good. Moving forward, everybody, from here I can write it as log r divided by r naught is equal to minus kt divided by 2.303. Can I also write it like this? Yes. Now if I equate this equation with y is equal to mx plus c, if I equate this equation with y is equal to mx plus c, then what will I get? Then what will I get? Then I will get a graph like this. See, here is your time. Here is your time. Yes, Sandhya Kumari, what is your doubt, bacha? Both order and molecularity depends on slow step in complex reaction. Yes, bacha. Yes. I have written the definition and all of these. No, I think you were a little late to the class. Order and molecularity. Molecularity is applicable only for elementary reaction. Molecularity is not applicable for complex reaction at all. Order is applicable for complex reactions. Sandhya bacha, I think you are a little late to the class, but no worries. Chalo, I have explained your doubt, right? Chalo, guys, come back, everybody. Yes, come back. Very good, Monish. Very good. Yes. So here I am going to take here log r naught divided by r. If I take like that, then my slope is going to be like this, and this is my slope. My slope is what? Slope is equal to, who wrote it? Somebody wrote the slope, right? Somebody wrote the slope. Slope is equal to k divided by 2.303. Is that right? See here, from this equation I'm writing it this. From this equation I've derived this. Acha, this can also be written as log r naught divided by r is equal to kt divided by 2.303. See, negative sign has been vanished. You did not see the y-axis. Look at the y-axis, look at the slope. Look at the y-axis, then look at the slopes. See, I have changed this thing. I have changed the y-axis. See, this is what I have done now. This is what I have done. क्या बात है रोहित, वेरी नाइस. एग्जाम हॉल में भी जाके यही करना, ठीक है? 4 बार क्यों, 10 बार कर लेना आप एग्जाम हॉल में जाके, बढ़िया रहेगा, मार्क्स मिलेगा आपको, 10 बार करने के मार्क्स मिलेंगे. नो मोनिश, check it out bacha, check it out. I have changed the y-axis. I have changed the y-axis. Sign has been changed. Sign has been changed. Yeah. So it's no longer going to be negative symbol. Yes, the slope is not going to be negative anymore. Now guys, we come across something called as half-life. What is half-life? From the name itself, you can understand the time in which the concentration of the reactant is reduced to 1/2 of its initial concentration, right? How do you denote it? You denote it as T half. Yes. Now T half for zero order reaction, everybody. Yes. You can't understand the graph. Sabarish bacha, can you go back and please do this again? You all know now how do you draw the graph. See, I do not know so much of mathematics, but I know that you know the mathematics. Whatever equation you get, you always equate it to y is equal to mx plus c, isn't it? Once you do y is equal to mx plus c, after that you draw the graph, isn't it? So that is what we have done. The graph is very easy. Can you just rewind and watch it back again? All the derivation that we did, from there we have equated it to y is equal to mx plus c, and then we draw the graph. Hai na? Can you just go back and watch it again? If you don't mind, if you don't mind. Okay, thank you so much, bacha. Thank you so much. So, now T half for zero order reaction. Let us calculate it. See, for zero order reaction, okay, for zero order reaction, everybody, we know that it is rate. Rate is equal to Kr to the power 0. That means it is just K, right? That means it is just K, right? Now here we have minus dr by dt is equal to K. That means I can write that also. Yes, right everybody, right? Right guys? Yes everyone? This is clear? This is clear? Yes. Now from here everybody, everyone, see. Okay. So we are writing concentration of R is equal to, from that first reaction, from that first that we derived right here, see, check here, 0. This guys, R is equal to minus KT plus constant, right? Minus KT plus R naught we wrote, isn't it? Yes, so chalo, now we are writing this, okay? R is equal to minus KT plus R naught. Square bracket, sorry. Here, done. Okay? So that means, everybody, that means that what can we write? Now my KT is going to become T half, isn't it? My KT is going to become T half because here I can write it like this. See, so initial concentration is supposed to be half. Yes, initial concentration is supposed to be half, and this will be equal to minus KT half, correct? Yes. Plus I am writing this to be as R naught. Make sense or nonsense, everybody? Make sense or nonsense, everyone? Make sense or nonsense? Guys, tell me. This makes sense? Now moving on from here, everybody. Yes, Balaji, very good. But we are deriving that. That is exactly what I am deriving right now to show you that zero order reaction does not depend on concentration. You will check it out. Now from here I can write that KT half is equal to R naught minus R naught divided by 2. Yes, right? Right everybody? Okay. Now what am I writing here is KT half is equal to R naught minus R naught. So understand it. 1 minus half will be equal to what? 1 minus half will be equal to what? Half. So can I write it as R naught divided by 2? I can write it like this. Correct? So that means my T half is equal to R naught divided by 2K. Can I write like this, guys? Can I write like this? And this is the T half for zero order reaction. This is how you calculate the T half for zero order reaction, and this is the formula. Yes, Amar, what is your doubt, bacha? Yes, Amar, what is your doubt? What are you guys saying? Wait a second. T half for zero order reaction, we have derived it. So this is what? This is your rate constant. This is your initial concentration. Guys, for zero order reaction, T half depends on initial concentration, by the way. Okay? Depends on initial concentration. Yes, depends on initial concentration. Don't confuse me. Wait up. I'll tell you about each of them. Okay? Now let us calculate half-life for first order reaction. Okay? For first order reaction half-life, let us calculate. Okay? Once again everybody, what is it that we know? We know that rate is equal to Kr to the power 1, right? That means I can also write it as minus dr divided by dt is equal to Kr to the power 1. Yes. Now from the integrated law, guys, from the integrated law that we calculated, from there we know that 2.303 divided by t log of R naught divided by R is what we had. Yes. Now from here, from this equation, what can we change? We can change it to see K is equal to 2.303 divided by T half. Yes, log of R naught divided by R naught divided by 2. That is supposed to be the concentration, isn't it? That is supposed to be the concentration. Now from here, see, so my T half is equal to 2.303 divided by K, and here log R naught by 2 here, that means it is log of 2, and from this we can calculate it and we get 0.693 divided by K. So T half is 0.693 divided by K. So for first order reaction, guys, the T half does not depend on initial concentration. It is independent of initial concentration. But T half is inversely proportional to the rate constant, that is K. Okay. Yes, T half is inversely proportional to K. This is also something that you get to see from here. Got it, everybody? Yes, guys? Yes. Now suppose we want to talk about the first order gas phase reaction. Okay, first order gas phase reaction. How do we calculate that, everybody? How do we calculate that? Amar, can you buy me? Can you buy me? Buy me, no? पूरे session में I'm trying my best to not scold you or anything. Meet me somewhere. The amount of abuses that you will hear me, no, you will get down on the floor. Ma'am, I have a doubt, ma'am, I have a doubt. And this is what you are asking. This is your doubt. This is called as parentless behavior. Your parents haven't taught you how to behave with somebody else. Don't you have a mom or sister at home? Do you ask them this question? I really hope I really hope you don't have a girlfriend, because if you do, oh God bless her. Oh God bless her, seriously. I really hope you don't have a girlfriend. In fact, you know what? I'll pray that you never find one. Die single. That will be the best. Really hope so. Please die single. It is so great. So great. Anyway, guys. Yes. So moving on, everyone. Moving on from here. Okay. Now, let us talk about, everybody, the last thing that I did not teach you, I guess. I did not teach you the gas phase reactions. Okay. So I'm going to change the heading here. This is, my dear student, first order gas phase reaction. Okay, first order gas phase reaction. This is what we are learning. Okay, this is what we are learning. Okay, chalo. So here we go. So imagine that suppose we have a very simple reaction. Okay, we have a reactant that is in gas phase, and this forms B in gaseous phase plus C in gaseous phase. Okay, for all of these we are going to write down the pressure of A. Here it will be pressure of B, and here it will be pressure of C. Correct, everybody? Great. Now at time is equal to 0, at T0 this will be P1 ATM, but here it will be 0 and 0, obviously, right? And right here, everybody, P total is going to be equal to P1, obviously, right? But at time is equal to T, what will happen? These two, there will be some formation. So here it will be X and X. But here I can write P1 minus X, isn't it? Here I can write P1 minus X. At this point, my P total is going to be P1 minus X plus X plus X. Yes, that means that P1 plus X, that is my actual total pressure, right? Now from here, what is going to be X? X is going to be PT minus P1, that is P total minus P1. Yes, everybody, can we write that? Now suppose I write here that pressure P1 minus X, which means that pressure of A is equal to P1 minus X. Am I right, everybody? Yes. Yes. This is P1 minus X, everybody. Am I right? Am I right, bacha? Yes? Okay. So if that is the case, that means, so here see, P1, can we calculate P1 from here? We can. And we have also calculated what is X, right? So I can write that, I can write this equation to be as P1 minus PT minus P1. Can I do that? Yes, I can do that. And from here, I can write it as 2P1 minus PT. Can I do this? Absolutely. I can write this also. I can write this also. Everybody. Now everyone, let us suppose that we want to find out K. So what is our K going to be? Our K is going to be 2.303 divided by T log P1 divided by PA, which is nothing but equal to 2.303 divided by T log of P1 minus 2P1 minus PT. Can I write that also? Yes. And this is an important formula that you need. Okay. Okay. All right. Yes, yes, Sandhya. Please tell me what is your doubt. So this is your last equation. And finally, guys, we come across pseudo first order reaction. Now, can somebody tell me what is pseudo first order reaction, guys? What is pseudo first order reaction? What is pseudo first order reaction? The second order reaction that somehow is made to behave like a first order reaction just by altering some conditions, like, you know, one reacting material is present in excess, or it's maintained at a constant concentration compared with other substance. For example, hydrolysis of ethyl acetate, that's a pseudo first order reaction, everybody. Okay, it's a pseudo first order reaction. What are you guys asking, Baba? Yes. If we take 2 moles of B, what will happen? 2 moles of what B? Then you change it, no? You change it here. Then you just have to change the equation. See, anyway, at time is equal to 0, the reactants will not be forming products. After at time is equal to T, you just have to change it as per the mole concept stoichiometric coefficient. But nobody is going to ask you that now. Nobody is going to ask you that, because that's a mole concept stoichiometric coefficient one. No one is going to ask you, bacha, now. Okay? Okay, Balaji. I hope I have explained. Anything else? What are you asking? Any other doubt? Monish, were you asking some other doubt? Monish, were you asking something else? Because I do not see. Okay, chalo. Acha. Now, in case of pseudo first order reaction, yes, everybody, you guys are right that a second order reaction, when it is made to behave like a first order reaction. Suppose, let us take, you have CH3, COO, C2H5, okay, plus you have water, okay. So suppose at T is equal to 0, what do you have? You have 0.01 mole of CH3, COO, C2H5. Here you have 10 mole of water, okay. This, when you have added some acidic medium, okay. Let's say you have an acidic medium here and it is forming CH3COOH, okay, plus C2H5OH. Guys, somebody, can you, Annai, see, Vandana has explained this to you, okay. Vandana has explained this. So at time is equal to 0, do you all agree that the product will be 0 and 0? Obviously. But at time is equal to T. Now what will happen? This will be 0. This, let's say, will be 9.9 mole. This will be forming 0.01 mole and this will also be forming 0.01 mole. Okay. Now, my dear students, what is going to be the rate here? The rate is going to be K dash CH3 COO C2H5. And here it will be H2O, because these are the reactants, right? So rate can also be equal to K CH3 COO C2H5. Yes, where I can write K is equal to K dash multiplied with H2O. Am I right, guys? Look at this. Look at the derivation and tell me, does this make sense to you? Just look at the derivation and tell me. Done? Sandhya, I did the derivation, no bacha. How come after doing the whole derivation you are asking me this doubt, bacha? Huh? How come you are asking me this doubt? I've explained the whole derivation. Please check that out. Okay? After doing the whole derivation, we have come to that conclusion that T half depends on concentration for zero order reaction. I've done the whole derivation. Rewind and watch it. Okay? Alright, it does. Now let us take a look at energy profile diagram. We are almost at the end, guys. We are almost. Amit Bacha, please watch yesterday's session. You will be able to find it. Okay? Not today. Today we are doing physical chemistry. Okay? Today we are doing physical chemistry. Alright. So everybody, till now, what are the things that we have studied? Till now, we have studied that what is chemical kinetics. What do we do here? We find the average rate. We find the instantaneous rate. Yes. After that, we spoke about the difference between order of reaction and molecularity of reaction. And we found out that molecularity of reaction is only applicable for elementary reaction, whereas order of reaction is applicable for both elementary reaction as well as complex reaction. Okay. Alright everybody, after that we took a look at some of the examples, then we did integrated rate equation, we draw the graphs for everything, then we derived the equations for half-life, we also studied about a pseudo-order reaction, and now we are going to take a look at energy profile diagram. This is going to be easy everybody, you just have to pay a little attention everybody, so please pay a little attention, okay? No, derivation nobody will ask in CBSE exam. But see, Sandhya had just asked me, right? Sandhya just asked me that, ma'am, how come in case of integrated rate law, we saw that zero order reaction does depend on concentration. But how come T half does not? For this, I actually did the derivation and I showed it to you that this is how it does not depend. So do you understand everybody? Why I'm trying to explain it to you? This is why. Okay? Now for energy profile diagram, guys, we have two cases. We have case one, which is exothermic reaction, let's say, okay? You have exothermic reaction, okay? All right, where this is delta H is equal to minus negative, yes? And here, guys, you have case two. Case two is your endothermic reaction. Case 2 is your endothermic reaction, where here delta H is equal to positive, everybody. Achha. Now guys, tell me, if I draw the graph, okay, suppose I draw the graph somewhat like this, okay? Imagine that the graph is like this. Graph is like this, okay? All right. Now, for the reaction to happen, guys, do you all agree that I will actually have to take the reactants to this position? If I take it to this position, then the reaction will happen. Am I right, everybody? Yes? Am I right, everybody? Am I right, everybody? Yes, guys? Yes? So the EA means activation energy. So if I take the reactants, I have to activate them for them to react, right? I'll have to activate them to let them react, isn't it? Monish, please wait up, bacha. Please wait up. Please wait up. I'll tell you all of it. Please wait up. Don't make my life harder than this. Okay? Yes, I'll tell you. Okay? So here, guys, check it out, everybody. Check it out. Here, what am I writing? Can I write this with pink? Yeah. See, here what is happening is this particular point, this is my activation energy of forward reaction. And this particular part, okay, this is the activation energy of the backward reaction. For the reaction to go backward, everybody, then I'll have to bring the product to here, then it can react. Correct, everybody? Are you guys understanding, everyone? Are you guys understanding here? So right here everybody, this is your ER, energy of the reactant, and this right here is the energy of the product. Yes, yes, all right. And this, my dear student, this particular point, okay, this particular point, this peak, this is your threshold energy. This is your threshold energy. What is EA? EA is the activation energy that is needed for the reactant to get activated. For a complex transition state. Now they are going to, from reactant, they are going to form product, isn't it everybody? Now for now for you to form the product, okay, let's say that you have taken hydrochloric acid and sodium hydroxide. You want them to mix up together and form sodium chloride and water. So they are going to go through a complex transition state, isn't it? They are going to go through a complex transition state. You have to activate this reactants. You have to activate this reaction. Guys, look at the diagram. Look at the heading. It says energy profile diagram. Study the diagram. Study what I'm teaching you. Now he has come on dancing on ma'am formula for threshold. No one is going to ask you this. This is energy profile diagram. You just have to know the diagram. That's it. Okay? So you have to activate them. For you to make them react, Arey Baba, you have to give them some energy, no? You have to give them some energy, right? You have to give them some energy, isn't it? So what will you do? To activate them, you have to activate them for them to react and form the product. So you have to take them, give them some energy, and then the reaction will happen. This is what the graph says. This is what the graph says, everybody. Do you guys see it? Do you guys see it now? Now do you guys see it, everybody? Yes or no, everyone? Very good. Very good. Now, if you have an endothermic reaction, I have to come this side, right? If you have an endothermic reaction, everybody, let me draw this here. Let me draw this here, okay? Yes. So this is your reaction coordinate. Now here what will happen is, this is your graph like, okay? This is your graph like, okay? All right, everybody. So understand this, everybody. Understand. Let's say that this is your potential energy, PE. Okay? This is going to be your threshold energy, isn't it? Yes, this is your threshold energy. Here is the product forming. So this is our EP. Okay? Here is the reactant. This is where the reactants start from. So this is going to be your ER, isn't it? This is going to be your ER. Now, what is going to be my EA activation energy? This part is my EA activation energy of forward reaction. And right here, this is the activation energy of backward reaction. Are you guys getting it? Are you guys getting it? Not clear diagram. Don't study. Don't study. You have never seen this diagram in your book. Huh? 3 दिन में एग्जाम है, आज आके मैं जो डायग्राम ड्रॉ कर रही हूँ उसको बोलो कि नॉट क्लियर. वाह. Do you guys get it? Yes, guys? Do you guys understand? This is clear? Krisha, you understand? Monish, do you understand, bacha? Please tell me, those of you who are studying, you let me know. Do you guys understand what is endothermic and exothermic reaction? In case of exothermic reaction, what is happening? Heat is evolved. Yes, heat is evolved. In case of endothermic reaction, what happens, guys? In case of endothermic reaction, what happens here? Why gap between ER and EP? Sandhya, bro, bacha, what are the doubts that you are asking? Sandhya Baba, tell me something, bacha. Okay. The reactants were here, right? Yes. Now you gave the reactants a little bit of energy. You have given them activation energy. Once they form the products, they are going to be even stable. The energy is going to be low, isn't it? The energy is going to be low now, bacha. So obviously, energy of reactant and energy of product, they will be little difference. I mean, come on, Babu. You have studied all this in class 11. Don't make your life so hard, no. You are in class 12 already. You can't do this. You cannot do this. Please understand all of these things. Okay? You know it. In chemical bonding chapter, you have read already, when the bond formation happens, there is less energy, hence they are more stable. So here also, at the reactant stage, they had a little bit of energy. You had to give them a little bit of energy. Then the reaction happened. Once the product is formed, they have come down. Right? Come on. Okay guys, now we are going to take a look at dependence, temperature dependence of rate, everybody. Temperature dependence of rate, and at this point everyone, we come across something that is called as Arrhenius equation. Okay, we come across something that is called as Arrhenius equation, everybody. Okay, alright, yes, okay, we come across something that is called as what? Hari, I do not understand your doubt. What is your doubt? I really cannot understand. What is your doubt? So here, Arrhenius equation, what does it say? It says that K is equal to A e to the power minus EA divided by RT. Here, R is the gas constant. Do we all know this? R is the gas constant. Yes, what is T? T is the temperature. What is EA? We have just studied. EA is your activation energy. EA is your activation energy. Alright. What is A here? A, my dear student, is Arrhenius. Arrhenius factor. Alright. Or it is called as frequency factor. Or it is called as frequency factor. Or it is called as a pre-exponential factor. Okay, and what is K, guys? K is your rate constant. Okay, K is your rate constant. Okay, all right, everybody. Now, if we want to plot for Arrhenius equation, everybody, guys, it is already about to be 5. I can only give you 10 more minutes. After that, you have your organic chemistry class. So here, K is equal to A e to the power minus EA divided by RT. Now we can write ln of K is equal to ln of A plus ln of e to the power minus EA divided by RT here. Ln of K is equal to ln of A minus EA divided by RT. Can I write it like this? Yes, I can. So ln of K is equal to minus EA divided by RT. Sorry, divided by RT. No, not divided by RT, divided by R. And here I can write 1 divided by T. I can write it like this. Plus ln of A. I can write it like this. Now this, if we equate it to y is equal to mx plus c, then what will happen? Then what will happen, guys? Then after this, my graph will look like this. See, here I will take 1 by T. Here I can take 1 by T. And here I am going to take ln of K. Now what will happen to my graph? My graph will somewhat look like this. What will be my slope? My slope will be negative. So slope is going to be minus EA divided by R. And this part will be my ln of A. So this is the Arrhenius equation plot. Okay. Alright, everybody. Yes. Finally, collision theory and probability steric factor. I do not think that is included. Guys, can somebody tell me, everybody? Can somebody tell me, is a probability steric factor and collision theory, is it a part of your NCERT? Organic chemistry is postponed to 7 p.m. Acha, it is rescheduled to 7 p.m. Okay, then I will complete it. Chalo, I'll complete it. Or I will just call Durgesh ma'am once and I will ask her, because if she starts from 7 p.m, she will have to be, staying in the office for a very long time. It is there? It is included? I think it is deleted, guys. Only collision theory is there. I do not think you have probability steric factor, because that's a JE one. Collision theory must be there. Probability steric factor is also there. Quickly let me know, guys. What about probability steric factor? Collision theory is there, that I know. Only collision theory. That's what I thought so. You won't have a probability. Only collision theory, right, Monish? Yeah. Collision theory is there. Yes, okay. So what is collision theory? So guys, when something is reacting, yes, when something is reacting, everybody, you guys understand that the number of collisions per second per unit volume of the reaction mixture, that is known as collision frequency. Right? That is known as collision frequency. I mean, obviously, per second per unit volume. You have always known this, right? Per second per unit volume, isn't it? We all know this. So everybody, let me write this down here, that the number of collisions per second per unit volume of the reaction mixture is known as collision frequency. What did I say? How many number of collisions are happening in 1 second in 1 unit volume of the reaction mixture, that is called as your collision frequency. What is this called as? This is called as your collision frequency. Collision frequency is denoted by Z here. So suppose A is forming B, then my rate will become ZAB e to the power minus EA divided by RT. Okay? Alright, everybody? Are you getting it? Now, collisions in which molecules, they collide with sufficient kinetic energy, that is called as threshold energy, guys. That is called as threshold energy. And if there is proper orientation to facilitate breaking the bonds between the reacting species and the formation of new bonds, yes, and the formation of new bonds, that means the products are forming, then that is called as effective collision. Are Baba, obviously, right? Okay, let's understand this. See, imagine, okay, I have 2 specs box here, right? I have 2 specs box. See, what is happening here? If the orientation is proper, and these two are colliding with each other, they broke the bonds and then they form a new product like this. Okay? Then it is going to be called as effective collision. But if suppose they are colliding like this, then how are they going to form the bond? How are they going to form a new product? What is this? T-shape. What is this? T-shape of product formed, huh? No, right? T-shape of product formed cannot. Correct, everybody? Do you understand what am I trying to say? So if you have 2 reactants, okay, 2 reactants, their orientation is proper. See, orientation is proper. This way if they react. Now the collision will also look fun, right? See, imagine what happens, right? If let's say that 2 cars are coming, if they collide, and if they come near and then they go away, you will be anticipating that, oh, collision will happen, and it did not happen. You won't have fun. But if you see that they are colliding head on head like this, you will be like, whoa. You'll actually see, look at the accident, and you'll be like, wow, what just happened? So that is effective collision. Yes, that is effective collision. Okay, all right, everybody. Yes. For probability or steric factor, you only need the formula. So guys, the formula is rate is equal to, what you do is you add a probability factor or the steric factor, and then you add ZAB e to the power minus EA divided by RT. So this equation is modified from the Arrhenius equation, and that's it, everybody. Okay, this equation is modified from the Arrhenius equation, and that's it. And finally, guys, we have come to the fact that catalyst dependence of rate constant. We all know that what is a catalyst? A catalyst is basically that substance that can increase the rate of the reaction, but it does not undergo any permanent change in itself chemically. Okay? Now catalysts, they can increase the effective collision. The catalysts, they can reduce the activation energy. Remember, guys, this activation energy, this activation energy can be reduced when we use a catalyst. All right, with this note, we are done with this chapter as well, everybody. We are done with this chapter as well, everybody. Now, you guys, let us take a look at some of the questions, shall we? Yes, let us talk about some of the questions, everybody. First thing is, define rate constant. What is rate constant, guys? What is rate constant? Rate constant, everyone, is rate constant is the rate of reaction, when the concentration of reactant is unity. Okay, when the concentration of reactant is unity. Okay, all right, everybody. Second question, everyone. Second question is, express the rate of the following reaction in terms of the formation of ammonia. How do we do that? We want to talk about rate of reaction. Rate of reaction is equal to minus dN2 divided by dt. That means here we can see that it is going to be minus 1 divided by 3 dH2 divided by dt. That will be equal to plus half dNH3 divided by dt. Am I right? This is how it is going to look like. This is how it is going to look like. Yes, everybody? Yes, very good. Very good. Very good. Yes, this is done, guys. Chalo, moving on. What is meant by the rate of a reaction? Differentiate between average rate and instantaneous rate of reaction. Will you guys be able to do it? Will you guys be able to do it, everyone? Yes, I think we know this, right? I think we know this. Very good. Next, guys. Next. For the reaction, the rate of formation. For the reaction, the rate of formation of NO2 is 2.8 into 10 to the power minus 3 molar S to the power minus 1. Calculate the rate of disappearance of N2O5. How do we calculate that? How do we calculate it? From the reaction, yes, so you will have to write the reaction first, okay? First, write the reaction. Once you have written the reaction, then you will figure out that it will be 1 by 4 delta NO2 divided by delta T is equal to minus half delta N2O5 divided by delta T. That means that 1 by 4 NO2 is 2.8 into 10 to the power minus 3. This is equal to minus half delta N2O5 divided by delta T. So what is going to be the rate of disappearance, everyone? Rate of disappearance, can you calculate from here? What is going to be the rate of disappearance? You just have to calculate from here. From here you can calculate. Can you all calculate this, guys? Can you all calculate, guys? Write the reaction. You guys write the reaction. You don't know the reaction, huh? Bare. See? Who is telling me? Ma'am, write the reaction, it seems. I'm not writing the reaction. You write the reaction and tell me. You write the reaction and tell me. Okay. Show us writing the reaction. Bacha, what is the reaction? N2O5 forms NO2, right? What is the reaction? You tell me. You know this. Arey Baba, this is such... Just the equation you have to write. Just the equation. You don't know the equation. What are you guys telling me? What are you guys telling me? You're not getting marks in 1 mark. Chalo, theek hai, we will do that. Okay. You guys will surely, definitely, someday kill me, I guess. Chalo, here I will write it, okay? Here I will write it. What is the reaction, guys? The reaction is, everybody, N2O5 forms. What does it form? It forms NO2. Yes. Alright. It forms NO2 plus nitrogen dioxide plus it forms O2. Now what do you have to do? You have to balance it. How will you balance it, everybody? If we take here NO2, O5 here, so 2 and 2 here, right? We'll have to balance it. So how do we balance it, guys? Can we balance it, everybody? Angu, how did you calculate? How did you calculate? Now you just have to balance it. Can you balance it? Can you at least balance it? Or no? Can you guys balance it? Or no? Should I do that also? Should I do that also, or will you be able to balance it at least? Please tell me, guys. See, 4, 2 2s are 4, 4n here, and 2 5s are 10. So 4 2s are 8 already, 8 and plus 2 here, 10. This is how you balance it, okay? Now once you have balanced it, what do you have to do? Just calculate. That's it, we did. That's it, I did. That's it, I did. See, this is the reaction. So that is how I calculated 1 by 4, because this is the stoichiometric coefficient here, isn't it? And see, 1 by 2, because this is the reactant here. So here I have added minus, because rate of disappearance of N2O5. And after this, from here, guys, you can calculate what is the rate of disappearance. Is this clear? Is this clear or no? Is this clear or no, guys? Yes? Okay, chalo. Moving on from here, everybody. Next question is, for a reaction R to P, half-life T half is observed to be independent of the initial concentration of reactant. What is the order of reaction? Independent of the initial concentration of reactant, guys. What is it going to be? It is going to be first order reaction. Yes, this is going to be a first order reaction. So this is the kind of question that you are getting in your exam, everybody. Does this look nice? Yeah. Does this look nice? Yeah. Now, next question. Write the unit of rate constant for a zero order reaction. Who can tell me the rate? Who can tell me the unit, guys? Unit is mole liter to the power minus 1 s to the power minus 1, isn't it? Yes, very good, very good, very good. Chalo. Next is, for a reaction A to B, the rate of reaction becomes 3 times when the concentration of A is increased by 9 times. What is the order of reaction? This, can I give it to you as homework? Because I remember that somebody had asked me like this. This, can I please give this to you as homework? Please, 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 please. Will you do it? Will you please do it, guys? Will you please do it, everybody? Yeah? Can you all please do it? One question for homework. One question for homework. Okay? Please do this. I think you can do it. And the answer is also written here. So just try to solve it. Okay? One question. Okay. Next, for a chemical reaction R to P, the variation in the concentration R versus time T plot is given. Predict the order of the reaction. Guys, from here can be predicted. This R is given and T is given. This is a negative slope. What does this graph look like? This graph is definitely a zero order reaction graph, guys. Zero order reaction. We have done this. I have also drawn the graph for you, everybody. I've also drawn the graph for you, so I am hoping that you know this. Secondly, what is the slope of the curve, guys? The slope here is going to be what? Because I've just told you zero order. That means the slope is going to be minus k, isn't it? It is a negative slope. Negative slope, if it is negative slope, guys, then what is it going to be? We all know that rate is equal to k. Rate is equal to minus k. So here, that's it. So here, that's it. Very good. Yes, Krisha, very good, very good, very good. You guys are doing amazing. Now, next question, everybody, is if the rate constant of a reaction is k is equal to 3 into 10 to the power minus 4 s to the power minus 1. Identify the order of reaction. By the way, guys, the moment you see that this is the this is the unit. Now you tell me, what is it? Concentration divided by time. Yes, divided by time divided by rate to the power 1. Yes, that means that it is concentration divided by time multiplied with 1 by concentration. So calculation cancelled 1 divided by time, that means s to the power minus 1, and this is for first order reaction, isn't this? This is for first order reaction. Absolutely correct. Absolutely correct. Yes, you guys are right. Next question. Define the following terms. Pseudo first order reaction, I think you can do this. Half-life period of a reaction, I think you can do it. These are all previous year question, guys. These are all previous year question. Okay? Alright, and finally we are done with chemical kinetics. Now who all are ready for electrochemistry? Okay. Now everybody, you guys tell me, do you want me to finish electrochemistry right away, right now? Or should I record the session of electrochemistry and post it tomorrow right in the morning? You tell me, do you have the capacity? Do you have the capacity to study more of this? Because after this you also have organic chemistry. You tell me, whatever you tell me, I will do this. Whatever you tell me, I'm gonna do this. Do you want to load in more and study it right now, or should I record it and tomorrow morning I can give it to you? Vote, guys, vote. Ready now? Some of you are saying ready now. Some of you are saying no, you can complete it. Can we have a bit of a break? Tomorrow morning, no ma'am. Record. Morning time, ma'am. No ma'am. Today, first order I've taught you already. Post recording, break. Now we will do it. Yeah, exactly. Evening, again you have organic reactions, organic also. You also have organic. So that is why I am asking you, because again this will take me another 1.5 hours at least. Should I record it and send it to you? Might be a little difficult. Might be a little difficult for me to, take right now. Guys, majority of the students are telling me to record it. So shall we record it then? Majority of the students are telling me to record it. So can we just record it then? Yeah, some of the students are telling me that we have to take a break, electrochemistry. Okay, let's do one thing. Okay, let's do one thing, guys. Let's do one thing. Chalo. First of all, let us take a 10-minute break. Okay, let us take a 10-minute break. By that time, I will also ask Durgesh ma'am if she wants to, prepone her class a little bit, then she can do it. Okay? Okay? Yeah. Let's take a break. Let's take 10 minutes break. After that, if you still feel like taking the session, I will do it. Otherwise, we can leave it. Okay? Yeah, I'll teach you now. But let's take a 10-minute break, guys. I also need to sit for a while. Okay? I also want to sit for a while. I'll do it now. Yes. I'll do it now. No problem. No. I'll post it today only. Let's finish it off today, guys. Let's not leave it for tomorrow and all. Let's do it today. But let's take a 10 minutes break now. Okay? Yeah. I'll teach you now. Whoever wants to study it tomorrow morning, you can do it tomorrow morning. Let us just wait for some more time. Yes. See you after the break, guys. See you after the break. Okay? After the break. Bye. All right, guys, the last chapter, everybody. Are we ready? Another 1 hour, maybe another 1 hour, and we will be done with electrochemistry as well, everybody. Yes, are we done? Here we are. Everybody is here with me. Varsha, let's finish it. No, why keep it for tomorrow? See, anyway, on 27th you have the exam. Let's not keep anything for tomorrow. Let's not keep anything for, later on. Let's not procrastinate anymore. Let's do this. Okay? We need to revise this 2 chapters. You revise this 2 chapters at the end. Okay? Revise them tonight only. Tonight you revise them. Chalo. So electrochemistry, guys. When we are talking about electrochemistry is basically the study of production of electricity. From where? Production of electricity, that is from a chemical reaction. When a chemical reaction has happened, there has been some energy that is produced, and from that energy you are converting it to electricity. That means electrical energy. That is called as your electrochemistry. Look at the word, guys. You have electro, you have chemistry. That means there is electricity and there is chemistry, right? So whenever a reaction happens, you have some energy that comes out of it. That energy will be called as chemical energy. This chemical energy, when you can convert it to electrical energy, that will be your electrochemistry. Correct? Yes, everybody. Now, we are writing here spontaneous reaction. What do we mean by spontaneous reaction? A spontaneous reaction is that reaction which is absolutely happening on its own. You do not have to help it. That is called as a spontaneous reaction. So a chemical reaction sometimes is spontaneous. That means it happens on its own. So that chemical reaction provides you electrical energy. But you also have non-spontaneous reactions, basically those reactions in which you have to give some energy. For example, a non-spontaneous reaction, suppose that you give electrical energy and then you make a chemical reaction happen. Yes, so that will be a non-spontaneous reaction, right? That will be a non-spontaneous reaction. But I do not have a quiz. How do I conduct it right now? I will not be able to conduct it, okay? Yes, so in electrochemistry, we basically talk about electricity and chemical reaction. And by the way, before I start with the lesson, everyone, do you remember oxidation and reduction? Red cat, anox. Reduction happens at cathode. At an anode, you have oxidation. Guys, do you all remember this, everyone? Do you all remember this? Yes, red cat and ox. Reduction happens at cathode. At anode, oxidation happens. And what is oxidation? Oxidation is the loss of electron. What is reduction? Reduction is gain of electron. So this you can remember it as oil rig. Okay? Now, when chemical energy forms electrical energy, this, my dear students, can be a spontaneous reaction. Okay, what is this? This can be a spontaneous reaction. Alright, this is a spontaneous reaction. But when electrical energy is converted to chemical energy, for this, you will have to maybe switch it on. You will have to let the electrical energy first become. Let the electrical energy first be produced, and then from there you have to derive chemical energy. So this, my dear students, will be your non-spontaneous reaction. Okay, this will be your non-spontaneous reaction. Am I clear? Spontaneous and non-spontaneous, do we all know the difference, guys? Yes, do we all know the difference, guys? Yes, bacha, I will conduct a quiz. Don't worry about it. Okay, don't worry about it. Who is this? 𝐸𝐴𝐶. Left में oxidation, anode negative. What if examiner wants to just mess with your head और उन्होंने right में दे दिया oxidation, तब क्या करोगे? How will you do it? No. Remember what I'm telling you. Remember red cat and ox. Okay? Reduction at cathode, anode पे oxidation. And what is it? Now, next you remember it as oil rig. Oxidation is loss of electrons. Reduction is gain of electron. This is how you remember. Okay? Hi Shivam. Welcome to the class, bacha. Don't remember it as left and right. Left and right is not the thing that we're talking about. Okay? Alright. Now let's get introduced to something that is called as electrochemical cell. Guys, in mathematics, you must have heard about something that is called as, No, Ishan, I'm not going to teach you organic chemistry this year. This year, organic chemistry will be taught to you by Durgesh Nandini ma'am. I will try and teach you next year probably, but this year it will be Durgesh Nandini ma'am, because see, I am already, like yesterday I stood here for 5.5 hours. Today again I am standing for more than 5.5 hours. After this my body is giving up, bacha. I cannot take care of organic chemistry. Chemistry is very vast. We cannot do it all. Okay? We really cannot do it all. Okay? Okay. Okay. So in mathematics, do you remember this chapter called set theory? Everybody, do you all remember? Do you all remember, everyone? Set theory. In set theory, what have you learned? In set theory, you must have heard about something called as superset, something called as union of set, right? All of these you must have heard. A class of set, isn't it? Yes, 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 yes. You must have learnt about this, right? So the electrochemical cell, this can be called as your superset. Okay, this is your superset. Now in superset electrochemical cell, you have different types of cell. One, this is called as your voltaic cell or galvanic cell. Okay, same. Voltaic cell, galvanic cell, it's absolutely the same. Okay. The second one is your electrolytic cell, where what happens is the electrical energy is converted into chemical energy. That means that this is the non-spontaneous kind, and this is where you have the spontaneous kind of energy. Getting it, everybody? Yes, getting it, everyone? Now let us quickly come to electrochemical cell, everybody. Electrochemical cell, guys, this cell was actually discovered by someone named as John Daniel. Okay, his name was John Daniel, everybody. Yes. Now here, do you notice, everybody? Do you notice, everyone, that here you have a zinc rod? Okay, zinc rod you have. And here, suppose you have ZnSO4, that is zinc sulfate. Okay. Now what zinc does, no? What zinc does is, zinc gets converted to Zn2 plus, but by giving away 2 electrons. These electrons, they get accumulated here. Okay, these electrons, they get accumulated here. And after a lot of accumulation, what happens is they start traveling through this wire. Okay, they start traveling through this wire and they reach the copper rod. At the copper rod, these electrons are again getting accumulated. Okay, they are again getting accumulated. They are again getting accumulated. And here you have copper sulfate solution. Okay, here you have copper sulfate solution, which must have dissociated and it has formed Cu2 plus. This Cu2 plus now will grab 2 electrons and it will become copper and it will start getting accumulated here. Are you guys getting it? Are you guys getting it, everybody? What am I telling you? Are you guys getting it? Yes. So this is your Daniel cell. Here what is happening is copper 2 plus is gaining 2 electron and it is forming your copper. Okay. So now if I have to write down the reaction, guys, if I have to write down the reaction, I will write it down here better. So Zn forms Zn2 plus and it gives away 2 electron. Yes. So Zn, the zinc rod, it starts getting thinner and thinner and thinner, right? The zinc rod, it starts getting thinner and thinner and thinner. What is happening here? See, zinc is losing electron. And what did I tell you? I told you that oxidation is loss of electron. I've told you that. So if oxidation is loss of electron and you can see that zinc is losing electron, that means that this is oxidation. And if zinc is getting oxidized, that means this is happening at anode. Am I clear, guys? Yes, this is happening at anode. Very good. Okay, next. Now Cu, copper was 2 plus and copper grabbed hold of 2 electron and it formed copper. Okay. After some time, we see that the copper rod is becoming thicker and thicker and thicker, guys. Okay. The copper rod is becoming thicker and thicker, everybody. Now here you see that copper is gaining electron. That means this is the reduction. Am I right, everybody? And where do you see reduction? Reduction you see at cathode, right? You get to see reduction at cathode. Am I right, everybody? Yes. Now we see that, now we also notice, everybody, that electrons are flowing. Where is electron flowing from? Electrons are flowing, everyone, from anode to cathode. Yes, from anode to cathode electrons are flowing. That means electricity is flowing opposite, okay? So we can write here that electricity flows from cathode to anode. Okay, electricity flows from cathode to anode. Cool guys, can we write this? Yes. Now after some time you will notice that zinc, yes, zinc was forming Zn2 plus, isn't it? So after some time you will notice that Zn2 plus gets accumulated, Zn2 plus gets accumulated in the solution. Okay, Zn2 plus gets accumulated in the solution, right? And you will also see here what happens is, see SO4, Cu2 plus SO4 minus, right? SO4 minus gets accumulated in the solution. Am I right, everybody? So if this side Zn2 plus is getting accumulated and if that side SO4 minus is getting accumulated, you tell me after some time, won't the flow of electrons stop? It will stop, right? It will stop, isn't it? After some time, the flow of electron will stop because electron is negatively charged and Zn is positively charged. Zn2 plus is positively charged, so electron will be like, why should I travel so long? Zn is here. No, I will get back to Zn. The electron is negatively charged, this is positively charged, positive negative affinity, these two will get together. So at certain point we will see that if we have a bulb here, let's say that if we put a bulb here, we will see that the bulb glows for some time, after that it stops glowing. Why so? Now what do we need to do? What do we need to do? Now we need something else, okay? Now we need something else so that we can make the bulb, make the glow for a longer duration, okay? We want to make this bulb glow for a longer duration. So at this point, what will we add? We will add, as you can see, a salt bridge. So what is the salt bridge? The salt bridge is actually nothing but it is a glass tube, everybody. Yes, it is a glass tube which is U-shaped. It is U-shaped glass tube which is filled with salt and it is filled with a polysaccharide. Okay, it is filled with a polysaccharide and salt, and the polysaccharide, my dear student, is your agar-agar. Okay, agar-agar is gel-like substance. Okay. Alright, for example, if you take, let's say, if you take here KCl, then obviously KCl will be dissociating and it will form here K plus plus Cl minus. Now this K plus, it will attract the SO4 2 minus ions, okay? And this Cl minus, it will get involved with the Zn2 plus ions. So that way, what will happen is the zinc 2 plus ions, they will vanish. The SO4 2 minus ions will also vanish and the flow of electric current will continue, okay? And the flow of electric current will continue. Very good. Okay, everybody. Now, here we can write, so what does the salt bridge do? The salt bridge, it completes the circuit, my dear students. What does it do? It completes the circuit, hai na? It completes the circuit. What does it do? It reduces the junction potential. What is junction potential? What is junction potential, everybody? Junction potential is basically this Zn2 plus, Zn2 plus, Zn2 plus was getting accumulated. Yes, SO4 2 minus, SO4 2 minus was getting accumulated. This is called as junction potential. Your junction potential was getting disrupted, right? Now here you have the junction potential that is reduced. It also tries to maintain electrical neutrality, okay? Maintains, everybody, what does it maintain? It maintains electrical neutrality, okay? It maintains electrical neutrality. Got it, everybody? Is this clear, guys? Is this clear? Yes? Very good. Now, everybody, let us come to something that is called as the redox couple. What do you mean by redox? Redox is reduction is happening, oxidation is happening. What is couple? Couple means there are two. So all this while, did you see that we had two containers here, right? We had two containers here. One where Zn is getting oxidized to 2 plus. One where copper is getting reduced, isn't it? Yes. So one part can be called as the oxidation half and the other part can be called as the reduction half. If we combine these two half cells, can we call this to be a redox couple? Absolutely yes, everybody. Right, guys? Yes, absolutely yes. All right, everyone. Yes. Okay, guys, do you understand what is the redox couple? Redox couple is basically combination of combination of two half cells. Okay, combination of two half cells. Bole to the reduction half and the oxidation half. When you have combined, it becomes your redox couple. Okay, all right. Now, anode to cathode electrons flow. So, why is it flowing? Why do you think that anode to cathode electrons are flowing? Are Baba, there is potential difference, isn't it? If there is no potential difference, then how will the electrons flow? It will not flow. So anode to cathode electrons are flowing because there is a potential difference. And let us assume that the potential difference here is E. If the potential difference here is E, can we apply external potential? Let us apply external potential, okay? Let us apply external potential, and this time let's name it as E external, and this E external, this is opposite to your this is opposite to the potential that you have here, okay? This is opposite to the potential that you have here. So now what will happen? You can have three, you can have three scenarios here. Number one scenario can be everybody. Let's suppose that your E external is lesser than your potential. Okay, your E external is lesser than the potential difference. Then what will happen? The electron will flow as usual. The electron will flow as usual. And how are the electrons flowing, guys? The electrons were flowing from Zn to Cu, isn't it? Electrons were flowing Zn to Cu. Very good. Now, by chance, if you have E external and let's say that is equal to E, then what will happen? There will be no flow of electron. Am I right? Very good. Now, third case can be that your E external, it is greater than electron. Then now what will happen? Now, electron will flow opposite. Electron will flow from copper to zinc, isn't it? And at this point of time, we start calling this to be as electrolytic cell, which is what Krisha was telling us from a very long time, okay? All right, everybody, is this clear, guys? Now let us quickly take a look at cell notation. So representation of cell. How do you represent a cell? How do you write it that this is a cell? How do you understand that this is a cell? Chalo, let us talk about it. So representation of cell, my dear student, is done as, check it out here, representation of a cell. Okay, representation of a cell, it can be done as, suppose we are taking the example of that zinc and copper wala cell, okay? Suppose we want to take the example of the zinc and copper. So we can write it as Zn. Zinc was in solid because it was the rod. It was forming Zn2 plus by giving away 2 electron, right? So here I am writing aqueous, okay? I can do that. After that, there was salt bridge. This salt bridge will be written as 2 parallel lines, okay? Then we know that copper in the solution was Cu2 plus. Yes, it was in the solution, so aqueous medium, and it was forming copper solid by grabbing hold of 2 electron. And if you want to make it more information based, then do you notice here, everybody, do you notice that you can also write aqueous 1 molar? Here you can write, see the phase boundary, see you can write here 1 atmospheric pressure, 1 molar, you can write that it is solid, it is gaseous. You can write all of these to make this even more better, okay? To make this even more informative, you can do this. Okay, guys? Understood, everybody? Till here, is it all clear, guys? Till here, is it all clear? Till here, is it all clear, everyone? Is it all clear? Now for calculation, do we need to write the exact? I think you need to write the exact answer. Not very sure. Yes. Right? Okay. All right. Now let us move on towards electrode potential. What is electrode potential? It is the potential difference that is developed between the metal electrode and its ions in solution. Okay. Now here we know that cathode has a positive potential with respect to solution. Okay. Writing it down here, cathode has a positive potential with respect to the solution. Alright. And anode has a negative potential with respect to solution. Are you guys getting it, everyone? Yes, are you guys getting it? Okay. Alright, everybody. Yes. Now electrode potential, right? According to IUPAC, we are always supposed to take into consideration the reduction potential, guys. We are not going to take into account oxidation potential. We are always going to write reduction potential, and that we denote it as E0, okay? Now, what is standard electrode potential? The standard electrode potential, everybody, is that the potential difference that is developed between the metal electrodes and the solution of the ions when there is unimolar concentration, unity bar, that is 1 bar pressure, 1 molar concentration. That means both of them have to be at unity and at a particular temperature. The particular temperature, my dear students, is your 300 Kelvin, and this is 1 bar pressure, 1 molar concentration, and that is called as unity. Got it, everybody? This is called as unity. Okay, this is called as unity. All right, everybody. Now, for oxidation potential, how do you write oxidation potential, guys? You write oxidation potential as, everyone, whenever you see oxidation potential, it will be written as M2M plus. Okay? And how do you write reduction potential? Reduction potential is written as reduction potential is written as E0 M plus 2M. Okay, M plus 2M, this will be your reduction potential. What is oxidation potential? Oxidation potential is the electrode potential for oxidation half reaction. It has a tendency to get oxidized, and it is greater is the oxidation potential. That means that the tendency for the substance to get oxidized will also be more and more. Okay. Alright, everybody. Similarly, for reduction potential, this is the electrode potential for the reduction half. It has a tendency to get reduced, and greater is the reduction potential. That means that it wants to get reduced even better. Okay, guys? Alright, everybody. Is this clear, guys? Do we understand this? Do we understand this, everyone? Yes? Very good. Chalo. Chalo. Now, everybody, let us take a look at cell potential. Okay, what is cell potential? Cell potential is basically the difference in the electrode potential of the oxidation half and the reduction half. That means that we can write cell potential as, everybody, okay, E cell is equal to E right minus E left. But tell me something, do you really want right and left? Do you really want right and left? No, we do not want right and left. Come on, it is science. Why will we write right and left? We want to write it as E cathode minus E anode. Right? Right, everybody? And one more thing that we want to know is that this is also called as the cell EMF. What is it called as? Cell EMF, that is electromotive force when no current is drawn through the cell. Okay? When no current is drawn through the cell, at that time you call this to be as EMF, and EMF of the cell, it must be positive. Otherwise, it means that it will not be feasible in the given direction. Okay? It will not be feasible in the given direction. Alright, everybody? Yes? Okay, guys? Chalo. Now, let us talk about cell potential or cell electromotive force. How do you measure it? You measure it in volts, guys. It is measured in volts. Okay? It is measured in volts. Okay? Cell potential, how do you denote it? You denote it as E cell. That's it. That's it that you have to talk about. Okay? That's it you have to talk about. Okay? Now let us come across something that is very important, and that, my dear student, is your standard hydrogen electrode, everybody. So what is this standard electrode potential, everyone? Just give me a second, everybody. Till then, just look at the picture. Just look at the picture. Do you understand anything? Just look at the picture, guys. Just look at the picture. 1 second. Sorry. One more second, guys. One more second. Why no current is drawn through the cell for EMF? No, we are saying, what we are saying is EMF of the cell has to be positive, okay? Otherwise, it will not be feasible in given direction, correct? Apart from that, one more thing I said is that cell EMF, when is it cell EMF? When no current is drawn through the cell. That means cell is chemical energy is getting produced, but you are not taking the electrical energy. You are not drawing the current. At that point of time, this is called as the electromotive force, because if you draw the electrical energy na bacha, then it will be reduced, right? From the chemical energy, whatever electrical energy you are getting, if you draw the electricity, it will be lesser. Correct? Do you understand, everyone? Do you understand, everybody? So exactly what I mean. So when you are not drawing any electricity from the cell, at that point you will get the correct measurement of cell EMF. Got it? Got it, everybody? Yes? Yes, guys, clear? Chalo. I'm so sorry, anime. I'm so sorry. Yes, I should have done that. I'm really sorry, bacha. I'm really sorry. I did not, think about that. I did not think about that. Sabarish, just explain, no? Did you understand now? Just explain, right? I've just explained that. Sabarish, did you not listen? I just explained, bacha. I just explained it. Did you not understand? Sabarish, quickly, can you tell me? Did you understand, or do you want me to repeat it again? Sabarish. Anyway, chalo, okay. Krisha, you understood, right? Sigma also understood. Okay, great. Okay, guys. Acha. You lost your connection. Okay, once again, bacha, see. The chemical energy is going to get converted to electrical energy, right? Yes. Yes. The chemical energy is going to be converted to the electrical energy, isn't it? Now, if you draw the electrical energy already, that means that whatever EMF of the cell, you will get a reduced reading of the cell EMF. Once you are getting from the chemical energy, you are getting the electrical energy. When no current is drawn, at that time you're going to measure the cell EMF. Got it? Got it? Yeah. Yes? I've just repeated, bacha. I've just repeated. Yes, Sabarish. Got it? Okay. Acha. Now, in case of the standard hydrogen electrode, or as we like to call it as SHE, that is SHE, right? Here what happens is you take a platinum wire. I know Sandhya might ask me, or somebody else might ask me that, Mom, why platinum? Because platinum can absorb hydrogen, okay? Because platinum can absorb hydrogen. That's why we use platinum and not something else. And here we will be using, my dear student, 1 molar hydrochloric acid, okay? What are we going to use? We're going to use 1 molar hydrochloric acid. So now what do we see? We notice that the cathode half cell reaction is going to be, the cathode half cell reaction, everybody, is going to be, cathode half cell reaction is going to be, acha, at cathode. So what is going to happen here? What is going to happen here? Reduction, everybody agree? You agree with me? This is your reduction is happening. And here you see that the reduction that is happening will be hydrogen H plus in its aqueous form plus electron, and it will form half H2 in gaseous form. Okay, it will form half H2 in gaseous phase. Now let us write the anode half cell. Let us write the anode half cell. That means that we are right now talking about the oxidation, isn't it? And the oxidation, my dear student, is going to be half H2, that is gaseous form. It forms H plus in aqueous plus electron, right? So now if I want to find out the reduction and the oxidation potential, I'm going to write it like this. See, E naught H plus half H2, this is equal to 0, and E naught H half H2 2 H plus, this is also equal to 0. This is also equal to 0. So this particular, guys, this particular electrode, that is standard hydrogen electrode, it is used as a reference electrode. Do you know why? Because you see, the oxidation potential as well as the reduction potential both are 0, and it can behave like an anode as well as it can behave like a cathode half cell. Do you understand? Do you understand, everybody? Yes, guys, that is exactly what is happening here. Okay? All right, everyone. So imagine that let us take this to be as plus and let us take this to be as minus. Okay? This side is plus, this side is minus. Okay? So then what will happen is this part will become cathode. This will become our anode. So at anode, we have connected the standard hydrogen electrode potential. Why is it 0? But that is the beauty of it. Because it is 0, that is why we use it. It's a fact. It's a fact. So there is no explanation to it. If you calculate it and if you notice, you will see that it is 0. That is the beauty of it, and that is why we can use it as a we can use it as a cathode or an anode. Okay? Okay? Samiksha, I do not think anybody is going to ask you the construction of sheet, guys. And if it is asked, it is right there in your NCERT. I don't think you want me to teach you. It's simple English explanation that you can write as it is. Please tell me, guys, do you want me to also teach you construction of standard hydrogen electrode? Do you really want me to teach you the construction of standard hydrogen electrode? Do you really want me to do that? Do you really want me to do that, guys? I suppose we can go a little further, but please quickly tell me, guys. Please quickly tell me. Do you want it or you don't? No, I can't see anything. I'll tell you, I'm coming to the voltmeter thing. Don't worry. Thank you. Thank you so much. Thank you. I'm not going to teach you that. It is just a simple line. You just have to take 1 molar hydrochloric acid in a container. You have to take some platinum wire, and you have to use a standard, and you have to use and nothing. That's it. That's it. That is exactly what is written in your NCERT, I suppose, because I know that I had seen it. You just have to write it as it is. Chalo yaar, now that you have told me, I think it's better if I take it only. Huh. See, it's right here. According to convention, a half cell called standard hydrogen electrode represented by this is assigned a 0 potential at all temperatures corresponding to the reaction. The standard hydrogen electrode consists of a platinum electrode, everybody. Yes, what do? The standard hydrogen electrode consists of a platinum electrode that is coated with platinum black. So first of all, you have to take a platinum electrode, you have to coat it with platinum black. Then what do? The electron, you will dip it in an acidic solution, okay, from where you can obtain pure hydrogen gas. Then the concentration of both the reduced and the oxidized form of hydrogen will be maintained at unity, 1 molar hydrochloric acid. Okay? This means that the pressure of hydrogen gas is 1 bar and the concentration of hydrogen ion in the solution is 1 molar. That is exactly what I've told you. Okay? Then, see, at 298 Kelvin, the EMF of the cell, that is standard hydrogen electrode, and second half cell constructed by taken this as anode and the other half cell is cathode. So that means that you can use it as a cathode, you can use it as a anode. Got it everybody? Yes? Alright, got it? So this you can write it exactly from your NCERT. You don't have to do anything else. Yes, Samiksha, understood bacha? Have we made it clear? Have we made it clear? Yeah? Yeah? Okay, bacha. Chalo. So now here, this side, that is the zinc rod, we are taking it as anode. Check it out. Chalo, check it out. Yes. And here we are taking the standard hydrogen electrode as the anode, everybody. Acha, now that we have taken zinc here, that means that what do we have here? We will have ZnSO4, correct? We will have ZnSO4 here. Am I right? Yes. What is this? This is the voltmeter, guys. This is the voltmeter. Okay. All right, everybody. So from this diagram that you see, okay, from this diagram that you see, everybody, tell me what you understand from here. What do you understand from here? From this diagram, we understand that standard hydrogen electrode has been used, and from here we want to calculate something. What is it that we want to calculate, guys? What is it that we can calculate, everybody? Chalo, let us calculate here. So now we know that here we want to calculate, let's say, E0 of cell. And we know that E0 cell will be E0 reduction potential of cathode. I told you that IUPAC convention we are only going to take reduction potential, not oxidation potential. Okay, so here you have E0 Rp cathode minus E0 Rp anode. Okay, Rp is reduction potential. Got it? Now here in the cathode part, what do we have? In the cathode part, guys, we have zinc, right? So we will write Zn2 plus 2 Zn. Remember, guys, this is a reduction potential. So Zn2 plus is getting reduced to zinc. Okay? Minus E0 H plus forms half H2. And that should be equal to 0. Okay? Because we know that this is 0. And we want that E0 cell to be is also equal to 0. So from here I can easily write that E0 cell is equal to E0 Zn2 plus by Zn. Am I right? I mean to say that this is equal to 0, guys. This part is just this part, okay? Just this is equal to 0, right? Just this is equal to 0. If this is equal to 0, that means E0 cell is equal to E0 Zn2 plus 2 Zn. Am I right, everybody? Very good. Very good. Okay. Now, according to the voltmeter reading, guys, do you see the voltmeter reading? What is written here? It is written 0.76. From the voltmeter, you can calculate and you can see. From the voltmeter reading, you will find that E0 Zn2 plus 2 Zn is equal to 0.76 volt. Alright, this will be 0.76 volt, and because it is positive here, but here we have taken this as a cathode, and we know that it is not Zn2 plus 2 Zn, actually it is Zn to Zn2 plus, isn't it? Zn to Zn2 plus, because this is cathode, so reduction is going on here. So we will write here minus 0.76 volt. Do I make myself clear, guys? Do I make myself clear? Yes. So Zn to Zn2 plus, can it happen? Yes, it can happen. Zn to Zn2 plus can happen, but tell me, Zn2 plus 2 Zn, can this get converted? Can Zn2 plus get converted to Zn? No, actually no. You will not be able to see this so much. You know why? Because hydrogen, H2, is more stable than the reduced form of zinc. And a metal which is less stable in its reduced form, it will not undergo reduction. Okay? It will not undergo reduction. Can you put separate video for PYQ, the most important MCQ and questions? Sailesh Bacha, can you focus in the session? No. Huh? Can you focus in the session? No, right? Why are you thinking about, future tense? Haven't I told you that that's my job? I will do it. Don't worry about it. Haven't I told you that this is my job and I will do it? I'll do whatever helps you. Can't you focus? How many times do I have to tell you the same thing? Now guys, now this is exactly from your NCERT, and here you can see that increasing strength of oxidizing agent. That means that fluorine here is the best oxidizing agent. And who was asking something about reducing agent, which is the strongest reducing agent? And here you can see that Li is the weakest. Li is the weakest oxidizing agent ever. All right? Yes. Li is the weakest oxidizing agent, whereas fluorine is the strongest oxidizing agent. Most of the time these values will be given to you, everybody. Okay, most of the time these values will be given to you. So if you see that from bottom to top, what is happening? From bottom to top, I mean top, at the top everybody, you have the best oxidizing agent. At the bottom you have the best reducing agent. Are you guys getting it? At the bottom you have the best reducing agent. So somebody was asking which one is the best reducing agent. It has to be Li. Li is the best reducing agent. Cool hai? Got it everybody? Yes. Nada, why don't you do this? Why don't you do this on your own? It's a question that you are asking. Like a proper question that I might have to solve and then do it. Huh? Why do I have to solve? You can solve it. No, I'm still teaching you the chapter. At least learn the chapter, then you can do it. Isn't the positive side anode and negative side is cathode? Please answer. See, again, if you keep doing this positive, negative, negative, positive, positive, negative, negative, positive, once again, everybody, reduction happens at cathode. Oxidation happens at anode. Okay? All right? Yes, everybody? Just remember this. That's it. Nobody is going to ask you which one is the positive side to tell me if this is cathode or anode. No. No. They are going to ask you reduction is happening where? Cathode. Cathode. Samiksha bro, yeah, please. Please don't ask me such basic question. Please. If you're coming to electrochemistry class, I am already assuming before your board exam, you know your redox reaction chapter from class 11. Please don't ask me such basic questions. If that is the case, then why am I not taking a marathon session of class 11 and class 12 both? I should be doing that only then. I'm taking electrochemistry, right? Let me stick to this. You can't, if you forget your basic, then it's not my fault. You have to remember those. I'm assuming that you know that. What are you asking? You know, right, which one is oxidant, which one is oxidizing agent. If it is an oxidizing agent, then what will it do? If it is a reducing agent, then what will it do? I mean, these are such basics that you know from a very beginning, bacha. What are you doing? Come on. Please get a little serious. See, look, please ma'am, electrochemistry. What am I doing? Am I dancing? What am I doing? This is what? Latin class or Greek class is happening here. Look at this, Nada. Ma'am, please, ma'am, electrochemistry, ma'am, please answer. My God. You guys are like proper crazy people. Proper crazy people you guys are. Chalo. Now, so all of these time, whatever we spoke about, right? Whatever we spoke about, these are all supposed to be in standard scenario. You have to have 1 molar concentration, 1 bar atmospheric pressure. But tell me something, every reaction that is happening around us, is it really happening in a standard form? No, right? Yeah. It is not happening in a standard form, correct? So if things are not happening in a standard form, now what are you going to do? Now what are you going to do? Now we need a different equation. I really do not like this equation, actually, to be very honest. I mean, both me and Pahul sir, we keep talking about this. Ki ye kyun hai? Why is this reaction there? Why is this equation there? Both of us do not like it. But anyway, we have to study because it's a part of your syllabus. So we have this reaction, or we have this equation called as Nernst equation. Basically, how do you write this Nernst equation? Let's have a look at it, everybody. So you write the Nernst equation as E m N plus, okay, and here you write M, okay. This will be equal to E naught, yes, E naught Mn plus M, okay, minus RT divided by NF ln, okay, M divided by Mn plus. All right, yes, okay, everybody. Cool, guys. Now, by chance, if you have a solid here, then the concentration of solid is equal to 1. Okay. And here, this will be the concentration of M. Okay. Now, here, what are the things that we know, guys? We know that R is your gas constant. R is your gas constant. T is your temperature. Yes. What is N? N is the number of electrons that are getting used up while reducing or oxidizing. Okay? And what is F? F, my dear student, is your Faraday's constant. Okay? F is your Faraday's constant, which is usually the number 96487 coulomb per mole, or sometimes it is given to you as 96500. Okay? This is what you write. Okay? Now everybody, I've just told you that imagine if this is a solid. If it is a solid, then the concentration of solid is equal to 1. If that is the case, then this equation, okay, it becomes E Mn plus M is equal to E naught Mn plus 2M minus RT divided by NF ln 1 divided by Mn plus. Can we write this like this? Can we write it like this? Yes. Can we write it like this? Yes, we can. Very good. Okay. But are we done with the Nernst equation? No. Now let us apply this Nernst equation in the Daniell cell. That is our copper and zinc wala dabba that we had. Yes. We had those copper and zinc, right? Copper and zinc, half container. Let us apply it there, okay? So applying this in Daniell cell at cathode, what will we get, guys? At cathode, what will we get? You will get ECU2 plus to Cu. Guys, do you see? Everywhere I'm taking reduction potential. That means that I'm only taking copper 2 plus is getting converted to copper. For zinc also I'm taking the reduction potential. Hence I will be writing Zn2 plus to Zn. But I told you that Zn can get converted to Zn2 plus, but Zn2 plus to Zn does not really happen. Okay. So ECU2 plus to Cu can be written as E naught Cu2 plus to Cu minus RT NF ln 1 divided by Cu2 plus. Notice it? Instead of N plus, now I have written 2 plus. Very good. Now for anode, let's see. For anode, we have E Zn2 plus to Zn is equal to E naught Zn2 plus to Zn minus RT divided by NF ln 1 divided by Zn2 plus. Can we write it like this, everybody? Yes, we can. Now everybody, yes. Now everybody, what are we going to do? We are going to write the E cell. So E cell is equal to E naught Cu2 plus cathode. See, cathode minus anode. Everybody, Cu2 plus to Cu minus E naught Zn2 plus to Zn. Right, everybody? Yes, very good. Now from here, these two equations we will mention here. Okay, these two equations. So how do we do it? E naught Cu2 plus to Cu minus RT by NF ln 1 divided by Cu2 plus. Am I right? This is how you can write it. Yes. And the second part, how will you write it? You will write it as E naught Zn2 plus to Zn minus RT divided by NF ln 1 divided by Zn2 plus. Can we write it like this? Yes, we can. Yes, we can. Right? Yes, we can, everybody. Correct. Now, from here, we are going to simplify this a little bit, okay? From here, let us simplify this and let us write it for E cell. E cell is equal to, now if we take common guys, okay, if we take this part and this part common, then what will we get? We will get E naught Cu2 plus 2Cu, okay, minus E naught Zn2 plus 2Zn. What is this guys? What is this? This is your E naught cell, isn't it? This is your E naught cell. Minus, we can take RT by NF to be common, okay? And here we will have ln 1 divided by Cu2 plus minus ln 1 divided by Zn2 plus. Can we write it like this? Yes. Acha. Now we have a property, right? ln of A minus ln of B is equal to ln of A minus ln of B, guys. Now what will happen? Can I write it as ln B by A or ln A by B? How do I write it, guys? How do I write it? Oh, thank you, Ria, but I guess it will come in some time, okay? I guess it will come in some time. Don't worry. ln A minus ln B can be written as ln A by B. Can I do this? Yes, everybody. Guys, are you understanding? Guys, are you understanding or no? What is wrong in the equation? Tell me. What is wrong in the equation? Tell me. I don't see that anything is wrong. Yes, brain power. Tell me what is wrong. Is there anything wrong in the equation, guys? Check it out. Anything is wrong? A by B only. That is what I have written. So what is the mistake here? Tell me, no, what is the wrong? Brain power, what is wrong? Guys, is there something wrong with the equation? What is wrong? If you're not telling me, then how will I understand? Yeah, chat is lagging. I know. No mistake, right? Brain power, then why are you telling that there is a mistake? There is no mistake. I've written it absolutely correctly. There is no... बच्चा मार खाओगे, समझ आ रहा है? हाँ, मार खाओगे, मार. हाँ, it's correct only, no? Anyway, okay guys, chalo, alright. Acha, now can we write it as E cell is equal to E naught cell minus RT divided by NF. Yes, RT divided by NF, we have taken it outside. Yes, so this is minus RT by NF, okay. And here ln A minus ln B is equal to ln A by B. That means we can write it as ln. Acha. Instead of writing it as A by B, what if I want to change it to B by A? If I do it B by A, then what will happen, guys? Then what will happen, everybody? If I do it instead of writing ln B by A, then what will happen? Guys, tell me, where is the mistake? Tell me, where is the mistake? I don't see there is any mistake. No, there is no mistake. Plus, very good. Yes. So if I do that, okay, if I basically, what I want to do is, I just want to write the denominator on the, yes, the sign will change. It will become plus, no, it will not become plus RT. So this is minus. This I have taken it out, okay. This I have taken it out already. ln of A by B, right? That means here this will become minus. if I write here ln b by a, if I write here ln b by a, that means that this should be minus, isn't it? Yes. So now everybody, if we check it out, guys, I think that I probably have made a mistake. Have I made a mistake? No. It doesn't look like a mistake. But I am facing an issue, guys. Please tell me, because we know that the product side as Zn2 plus it is supposed to be, and here it is supposed to be Cu2 plus. But how do I arrive at that? Because this is supposed to be the correct case. This is supposed to be the correct case. But in the Nernst equation, there is no plus, no. It is minus. So now tell me, we have to apply this log formula that I know. We have to use the log property. But actually, you know what? Nernst equation, let us check it out. From the book, it will be clearer. Guys, in the book also they have done this, and I do not know why. No, the log property though you have to use. That you can't help it. The log property you have to use. I got it. One second. I got it. Yes. This is ln of 1 by Cu2 plus. This is ln of 1 by Zn2 plus. The property is ln of A minus ln of B is equal to ln A by B, right? But what we have here is 1 by A and 1 by B, right? So that means that together when I take, see, this is 1 divided by Cu2 plus, this is 1 divided by Zn2 plus, and then when we use the property, it will actually, in the numerator you will have Zn2 plus, in the denominator you will have Cu2 plus. Yes. No. 1 by Cu whole divided by 1 by Zn. Very good. Yes. Okay, wait. Let me show you what happened here, okay? So this is ln of A by B, right? This is what? ln of A by B, isn't it? Yes? Yes, guys, right? So that means this can be written as 1 divided by Cu2 plus divided by 1 divided by Zn2 plus. That means that now I can write it as E0 cell minus RT divided by NF ln Zn2 plus divided by Cu2 plus. Got it? Yes, sorry, correct only. Everything is correct. Thank you so much, Vitesh. Thank you so much. Vitesh has also told the answer. Thank you so much. Yes, so this is the correct answer. This is how you derive it. Okay? So this is how we have derived the Nernst equation. Cool, everybody? Yes. Now, in general, let's suppose that if we have a general equation that is AA plus BB gives you CC plus DD. If that is the case, then your Nernst equation can be written as E cell is equal to E0 cell minus RT divided by NF ln C raised to the power C D raised to the power D divided by A raised to the power A and B raised to the power B. Okay, this is the general form of Nernst equation. Okay, Varsha, explain it again. Sorry, bro. No. 7 o'clock you have organic chemistry class. Cannot do it. They will not ask you any derivation mostly. I do not think so. Can you please rewind and watch it again? Please rewind it and watch it again. Okay? Now, where do we use the Nernst equation, guys? Where do we use the Nernst equation? We use the Nernst equation to find EMF of the cell. Whenever we want to find the EMF of the cell, that's when we use the Nernst equation. Okay? Alright? Yes, everybody? Cool? Now, do you see that this RT and F, they are all what? They are all constants. So if we calculate it, then our Nernst equation becomes E cell is equal to E naught cell minus 0.059 divided by N log, वही same thing you have to write, C to the power C, D to the power D divided by A to the power A and B to the power B. Okay, this is what you write. Now from this Nernst equation, you can also find Gibbs energy. You can also find Gibbs energy, guys. You can find Gibbs energy from this, from this Nernst equation. All right. Yes. Because see, we know that delta G is equal to delta H minus T delta S, isn't it? But we also know that delta G is equal to minus NFE cell. Okay. Minus NFE cell or minus NF E naught cell if delta G naught is being asked. So this is also an important equation. Okay. Apart from that, guys, you can also calculate equilibrium constant. Okay, you can calculate equilibrium constant. How so? Chalo, let me show you that also. See, for the Daniell cell that you had Zn2 plus and Cu2 plus, right? Zn2 plus Cu2 plus. At equilibrium, what do we know? We know that E cell is supposed to be equal to 0. Am I right? E cell is supposed to be equal to 0. All right? Yes. So if E cell is equal to 0, that means that E cell is equal to E naught cell minus RT divided by NF ln here Zn2 plus divided by Cu2 plus. Am I right? Yes. This is equal to 0, we already know, because at equilibrium this is going to happen, right? At equilibrium this is going to happen. Yes. Now from here we know we want to calculate, see, E naught cell minus, this is what, 2.303 RT, yes, divided by NF, and here if we change it to log, then we will write Zn2 plus divided by Cu2 plus, isn't it, guys? Yes. Yes, everybody. Yes. So this, we are saying that this is what, equilibrium. So that means that this will be your Kc. That means that this will be your Kc. Absolutely. So I can write it as E naught cell is equal to 2.303 RT divided by NF log of Kc. From here we can calculate 0.059 divided by N is equal to 2 here, because Zn2 plus Cu2 plus, right? So N is equal to 2 here, log of Kc. Can you calculate this? Yes. Can you calculate this? You can easily calculate it, right? So from here you can calculate the equilibrium constant, you can calculate delta G, you can calculate the EMF of the cell as well. Okay, guys? All right, everybody? Yes. Now we see that delta G is equal to minus NF E cell, that I have told you. What is F? F is 1 Faraday. 1 Faraday is charge on 1 mole of electrons. What is 1 Faraday? Charge on 1 mole of electron. Guys, this is such a super easy concept, and guess what? In JEE mains this year, you actually had a question related to just 1 Faraday. It was so simple and so easy. Now, condition for spontaneity of reaction. When is the reaction spontaneous? When you have delta G is negative and E cell is also positive. Okay. But if delta G is positive and E cell is negative, then you will have a non-spontaneous. If both of them are 0, then you will have equilibrium. And for standard condition, delta G naught is equal to minus NF E naught cell. Alright, everybody? Yes? Got it? Cool, guys. Moving on. Now let us take a look at conductance of electrolytic solution. Okay. What is conductance of electrolytic solution, guys? Let us quickly take a look at it. Asha, what do you mean by conductance? What do you mean by conductance? What is conductance, guys? Conductance definitely is basically ability to conduct, isn't it? Ability to conduct. What is resistance? Resistance is opposite of conductance, right? Resistance is basically you are not allowing the current to flow. That is called as your resistance, correct? How do you represent resistance? So if I write here resistance, everybody, how do you represent resistance? You represent it by capital R, okay? Or you represent it as by ohm, like this, okay? Now you can write the formula, capital R is equal to rho L divided by A. What is this rho, guys? This rho is called as resistivity. This is your resistivity, or you also name it as specific resistance. Yes, what do you name it as? Specific resistance, everybody. Cool here? All right, everybody. Yes. Now conductance is what? Conductance is just the opposite of resistance. Yes. So how do you represent conductance, guys? How do you represent conductance? You represent it as G. Okay. And then you can also write it as mho. Mho. Mho is basically nothing but ohm to the power minus 1. Or you can denote it as Siemens. S-E-I-M-E-N-S. Siemens. Okay. All right. Yes. We can also write it as ohm to the power minus 1 like this. So G is equal to 1 by rho A divided by L. This 1 by rho can be written as kappa. Kappa multiplied with A divided by L, and that, my dear student, is your conductivity. Okay? Now if we want to measure conductivity of an ionic solution, what does it depend on? It depends on nature of solvent. It depends on nature of electrolyte. It depends on size of the ions. It depends, again, this year in JEE, they had also asked you that conductivity of ionic solution depends on what? This was a question in JEE, guys. So easy. So easy. Yes. So conductivity of an ionic solution, what does it depend on? It depends on nature of solvent, nature of electrolyte, size of the ions, concentration of electrolyte, temperature increases, conductivity increases. Okay. All right, everybody. Yes. So how do you do it? How do you do it? You, everybody, you have a diagram in your book, right? You have a diagram in your book, something like this. Something like this, yes, right? And then you have like one electrode here, and like this, something like this, everybody. So you have a connecting wire like this, yes, connecting wire like this. Correct, everybody? So this is like this. This is like this, yes, right, everyone? These are what? These are your platinized electrodes. These are platinized electrodes. You have this, right? You have this. And here you have maybe ionic solution, right? So here how will you calculate it? You will calculate it as R is equal to rho L divided by A, obviously. And we also know that we can, rho is what? Rho is what, guys? Rho is 1 by, rho is, see, kappa is equal to 1 by rho. Kappa is equal to 1 by rho. So rho is equal to what? Rho is equal to 1 by kappa. Yes, that means that I can write this as 1 divided by kappa, L divided by A. And my dear bachu, can I tell you something? That this L by A, you know what this is called as? This is called as cell constant. Why? Because in a cell, in a battery, can you change the cross section and the length of the battery suddenly? No, you cannot. No, you cannot. Okay? Alright, everybody. Understanding, guys? Yes. See who is asking me. Hey, I'm teaching you chemistry, not physics. Wheatstone bridge is in physics. Here we just use Wheatstone bridge to measure something. That's it. Now, guys, we come across something that is called as molar conductivity. Now, what is molar conductivity? Yes, what is molar conductivity? To make conductivity more effective, we came up with molar conductivity. Molar conductivity has been introduced. So here we see that R is equal to rho L divided by A, right? This we are writing it as 1 divided by G, because this is what? Conductance. That means we can write it as 1 divided by kappa L divided by A. Yes. Now, kappa is equal to L divided by RA, which is equal to 1 by R, L divided by A. And this is equal to cell constant divided by R. Correct, everybody? Can we write it like this? Can we write it like this? Yes? Okay. Now in molar conductivity, it is basically the conductivity for 1 molar solution. Okay. What is it? How do you write it? You write it as lambda m. Why does this lambda look different? Because it is capital lambda. So this is equal to kappa divided by C. What is C? It is per unit concentration. What is it? It is per unit concentration. Okay. Alright, everybody. Yes, guys. Are we understanding? Yes. Are we understanding, everybody? Yeah. Okay. Alright. Here. Is there any doubt? Any doubt here, guys? Okay. No. Now we go across molar conductivity variation. Now molar conductivity, it increases when you decrease in concentration. Okay, when you decrease the concentration, molar conductivity increases, everybody. Okay, but conductivity increases with increase in concentration. Remember what I said? I said molar conductivity increases with decrease in concentration. Conductivity increases with increase in concentration. Now let's understand what is dilution. Dilution. Acha, chalo, theek hai. So let's suppose that we have a. Let's understand this. Suppose we have a cup here, guys. Okay, we have a cup here. In this cup, imagine that these are the only, these are the only molecules that you have. Okay, only molecules that you have. Now, if I dilute it more, if I add more water, am I changing the concentration? Am I changing the concentration? No. Am I using, do I have more amount of solute here? No. So if I'm diluting it, then what is happening? The number of ions per unit volume, that has decreased. Because I have only added solvent, bacha. I have only added solvent. I have not added solute. So the amount of solvent is increasing. That means that the solute, they have gotten to one corner and they are hiding now. So what is happening? Conductivity decreases. Conductivity decreases. Understood, everybody? Conductivity decreases. Yes? Alright. Getting it, everybody? Getting it, guys? Now do you understand this or no? Now do you understand this or no? Got it? Clear? On dilution, the concentration does not change. You are only adding more volume. Right? You are only adding more volume. So what is happening? The conductivity is decreasing. The conductivity is decreasing. So for a weak electrolyte, what is happening? Suppose you have CH3COH. You have acetic acid. Now acetic acid, we know that it does not dissociate completely, right? It does not dissociate completely. Why? Because it's a weak acid. So when the dilution increases, the dissociation increases now. Are you guys getting it? It's a weak acid. It's a weak acid. CH3COOH is a weak acid. Right? Yes? CH3COOH is a weak acid. So when you dilute it more, when you add more water, what is happening? Dissociation is increasing. Hence, for a weak electrolyte, the number of ions are increasing. The number of ions are increasing. But number of ions per unit volume still decreases, isn't it? Isn't it, everybody? Are you guys getting it? Yes? Hari, Krisha, are you guys getting it? Are you guys getting it now? Got it, everybody? What did I say? For a weak electrolyte, that is CH3COOH, it does not dissociate completely. But when you dilute it more, the dissociation is increasing. So yes, the number of ions are increasing, but the number of ions per unit volume is still decreasing. Nah. So that is what we said. I'm going to write the notes and send it to you. I don't feel like writing anymore, so just listen to me, okay? Then we come across Colruyt's law. So Colruyt's law is used to calculate the conductivity for mostly it is used for, a very weak electrolyte. Yes, for a weak electrolyte it is applicable better. Okay, for a weak electrolyte it is more applicable. Okay, na? All right, everybody. Yes, are you getting it? Ions increase for total volume. Exactly. Yes. So now for AXBY type, let's suppose that we have a molecule which is AXBY type solution. Here, if we want to find lambda equivalent at infinity, okay, what will we have? We will have 1 by Z plus lambda C. Sorry guys, very sorry. Yes, Krisha, you are right. Yes, you are right. Plus, here what happens? 1 by Z minus lambda A. This. What is CNA? CNA is cation and anion. CNA is cation and anion. Yes, everybody, are you getting it? Now for a weak electrolyte, if we try to do it, see, let's say that we have CH3COOH, which forms CH3COO minus plus H plus. Yes, all right, everybody. So at time 0, it will have C here and 0 here, 0 here. At time t, you will have C minus alpha, and here you will have C alpha, and here you will have C alpha, right? So if I want to find Ka is equal to, what will it be? It will be C alpha multiplied with C alpha divided by C minus C alpha, which is equal to nothing but C square alpha square divided by C multiplied with 1 minus alpha, which is equal to C alpha square divided by 1 minus alpha. Yes, and this, my dear student, is your degree of dissociation. What is this? This is degree of dissociation. Got it? Clear, guys? Yes, this is your degree of dissociation. The limiting molar conductivity of electrolyte. Yes, Varun, absolutely right. That is your Colrush law. Okay, guys. Now finally we come across electrolytic cell. Here we know that the external source of voltage is used to bring about a chemical reaction. That's what we said, right? We know here that delta G is equal to greater than 0 and delta G is equal to minus NFE cell, everybody. This will be positive when this is going to be negative. Cool? Yes, everybody? Yes, this is going to be negative. All right. Moving forward, guys, let us take a look at electrolysis. Guys, we only have 20 more minutes. We have to finish it quickly, as fast as possible. What is electrolysis? Electrolysis you have studied in a very, very, very younger class, everybody, when you are disintegrating, when you are breaking a compound with the help of electricity. That is called as electrolysis. So at cathode, what will you do? At cathode, you are going to use the object that you want to plate it. For example, if you have, let's say, tin. Yes, you want to plate the tin with gold. So tin has to be placed in cathode and gold has to be placed in anode, so that the gold is going to coat the tin. Got it? Electrolysis can be used to purify impure metal, and this you can read it. Okay, process of oxidation and reduction, what is electrolytic solution, how do you do electrolysis, and what are the factors that it depend on. All of that you can read on. Basically, I have already explained this to you, so I'm not gonna take some more time. Okay. Now Faraday's first law, I think I have just taught you in the formula wala session very recently. Faraday's first law is W directly proportional to Q, or we can write W directly proportional to IT. That means that W is equal to Z multiplied with Q, where Z is the electrochemical equivalence, right? Z is the electrochemical equivalence. Alpha is the degree of dissociation. Yes, sigma, yes. What is Faraday's second law? The second law says that the amount of different substances that are liberated by the same quantity of electricity moving through the electrolytic solution are proportional to their chemical equivalent weight. So Z is equal to equivalent weight divided by Faraday, that is F. Got it, everyone? Yes. And here is your cheat sheet, guys. The last cheat sheet, everybody, is right here for you. All right, have a look at it, check it out. I will be sending you the this thing. I will be sending it to you. Okay. And last but not the least, everybody, you have the batteries. Okay. In case of batteries, you have primary cells, those cells which you cannot recharge it, like the batteries that you have, the normal batteries, the dry cell and the mercury cell that you have. But there is also something called a secondary cell, which can be recharged. For example, the lead storage. Yes, for example, the nickel and cadmium cell. Fuel cells. What are fuel cells? Fuel cells are those cells in which energy is produced from combustion of fuels, and that can be converted into electrical energy. For example, the hydrogen and the oxygen fuel cell, right? That you have. Okay, and finally here you guys have a cheat sheet of your battery as well. What is in the dry cell? In the dry cell, what is the anode, what is the cathode, what is the electrolyte? So this will be very useful for your exam, I believe, right? This will be very, very, very useful for your exam, isn't it, everybody? Yes. Yeah, I don't want to teach a battery. No, I don't want to teach battery. Not at all. Not at all. I do not want to teach battery. Vitesh, do you want me to teach generator? Generator is there. Generator is there. You have primary battery, secondary battery, fuel cell, and corrosion. Corrosion also you have learnt it from your very, very, very young days, isn't it? Yes, that's it. That's it. Done with the chapter, guys. Done with the chapter, everybody. So, chalo. Let us take a look at. Okay, let us take a look at the questions, everybody. Acha, you said example. Sorry, Vitish. Sorry. sorry. Yeah, sorry. I thought you were telling me. Okay, the first question is define the following terms, that is fuel cell and limiting molar conductivity. Do I need to teach you this? I think you guys know. This is a previous year question. Both of these you know. Define the following terms, molar conductivity and secondary battery. See, this has repeated, guys. So please make sure that you know the definition. This has been repeatedly asked. Molar conductivity, limiting molar conductivity. They have asked you the definition once or twice, and it may come for 2 marks. Okay? It may come for 2 marks. So please check it out. Then what do you have? State Colruyt's law of independent migration of ions. Why does the conductivity of solution decrease with dilution? Just explained. This also we can do, right? So I'm only going to take care of the calculation part. If there is any calculation, then let's check that out. Okay? Let's check that out. Sir, chalo. Now, we got it. Calculate the degree of dissociation alpha of acetic acid. If its molar conductivity lambda m is this, given lambda naught of H plus is equal to this, and lambda naught of CH3COO minus is this. Okay. All right. No, infinite dilution. At infinite dilution, the molar conductivity is called as limiting molar conductivity. Yes, Krisha. Okay. I am on Instagram. You can find me, Hari. I am on Instagram, Nabamita, aka Nobita. It's there. So yeah. Okay, guys. So how do you calculate this? Very easy. Very easy, everybody. See, all you have to do is lambda naught CH3COOH is equal to what? Lambda naught CH3COO minus is the anion plus lambda naught H plus the cation. Okay. So here, what is the value? The value is given to you 40.9 plus H value is also given to you 349.6. So just calculate it. What will you get? 9, 10, 11, 12, 13, 14, 15. 15. So 5 here. 1. So 9, 1, 10. 10 is 0 here. 1. Then 4, 1, 5. And this, so 4, 4, 8. 1, 9. This is 9. And this is 3. That's it. Easy peasy. Biryani tasty. One second. Krisha, what did you ask me about? Vandana is saying something else. Because did I confuse you? Did I say something wrong? What did you ask me about? No, one second. Krisha, what did you ask me about? Sorry, bacha. You were asking me about limiting molar conductivity. Yes? Did you ask me about limiting molar conductivity, isn't it? Rohit Bacha, we are not doing organic chemistry yet. This is your physical chemistry class. Okay. So what did I say? I said that molar conductivity of a solution at infinite dilution. So yes, when you are going through infinite dilution, you have diluted it so much, that yes, the concentration of the electrolyte. Okay. So here, Vandana and Krisha, please make a note. Okay, you guys were telling me that when concentration is 0. No. Why am I correcting you? Please make a note of it, okay? It does not become 0. It approaches 0. It almost approaches 0. If you are appearing for other engineering exam, then don't write it is 0. It approaches 0. While you are calculating, you will write that yes, it is 0. Otherwise, you will not write. Okay? Alright? Yes. Yes, Sabarish. Yes. But that's what I clarified. So if you are writing for your JEE Vagera, you have to be very careful. Don't write it is equal to 0. It is basically how, you know, in your integration and differentiation, what do you say? Limit tends to 0, limit tends to infinity, but it is not exactly infinity. So when you are calculating, yes, you manipulate the data and you write that it is 0, but the definition says that it approaches 0. Got it? Yes. So Sabarish, Vandana. Acha, you said, oh, I'm so sorry then. My mistake. Sorry. Okay? Alright, everybody, guys, 10 more minutes left. Now, next question, everybody, quickly do it. Conductivity of 0.20 molar solution of KCl at 298 Kelvin is this much. Calculate its molar conductivity. How do you calculate it? How will we calculate it, guys? Again, it's going to be very easy, very peasy. So here, conductivity is given to you. This is your conductivity. This is your conductivity. Hai na? This is concentration of the solution, right? How do you calculate molar conductivity? Lambda m is equal to conductivity, that is kappa, multiplied with 1000 divided by concentration of the solution. Correct? Yes. Now, if that is the case, so what is kappa? Kappa is given to you, conductivity 0.025 Siemens centimeter to the power minus 1. Multiplied with 1000 divided by what is a concentration? It is 0.20. That's it. Calculate and put the answer. Okay. Netra, what are they asking? But they are asking for degree of dissociation. Where are they asking degree of dissociation? Acha. Okay. I want to do it faster, right? Okay. So now that you have calculated this, this is 390.5, right? Now all you have to do is, how do you calculate alpha? Alpha is equal to lambda m divided by lambda m naught. Now what is your lambda m? Given, no? See, molar conductivity lambda m is given to you 39.05. And you have calculated the lambda m naught right here. This is your lambda m naught. So you just have to calculate the alpha. You will find alpha. Got it, Netra? Yes? Why 1000? I mean, that's the formula, no? That is the formula. That is the formula. What formula did you use as it? You are given limiting molar, you are given conductivity, you are given concentration. Yes, you are given kappa. Acha, you have to calculate the molar conductivity. Calculate molar conductivity. Chalo, let's take a look at it. Ruko, I'll tell you. So, what are we doing here? See, you are given the temperature, you are given the conductivity of the concentration which is 0.20. So concentration is given to you, okay? All right, and kappa is given to you 0.025 s centimeter to the power minus 1. Okay? All right, everybody. Yes. Now we have to calculate what? We have to calculate, this is correct only, no? Isn't this correct? This is correct only, right? The formula for molar conductivity is 1000 multiplied with kappa divided by molarity. That is the formula, bacha. That is the formula. Okay. So we all know that, see, we all know that lambda m is equal to kappa divided by c, right? Yes? Yes? Now here, this is the case only if kappa is expressed in s meter to the power minus 1. But here it is centimeter to the power minus 1, na? That is why 1000. That is why 1000. Got it? How you find? Abey, it's given to you in the question. Guys, the numericals are not so tough. You're making it tough for yourself. You're making it tough for yourself. Paddy, what are you asking, bacha? And the concentration, yes, the concentration is molarity. That is given to you. So it is going to be mole liter to the power minus 1. Okay, wait up. Hold on. Let's check this out. I know that this is the formula. I do not understand that what yeah, Sanjay, you can do that. Yes. Wait a second. What happens to you? Lambda m is equal to k by c. Yes. Okay. All right. Molarity is given. If it is in centimeter to the power minus 1, then the formula for molar conductivity is lambda m is equal to 1000 multiplied with kappa divided by molarity. That is the formula. I can't understand, like, what is it that you guys are asking? This is the formula. So what you do is 1000 multiplied with 0.025 divided by 0.20. Once you get the answer, whatever is the answer that you get, this will be in centimeter square mole to the power minus 1. That's it. This is the conversion formula, guys. This is the fact. Okay. There is nothing else. That's it. Normally it is lambda m kappa divided by c only if it is given in meter to the power minus 1. Otherwise you write 1000 multiplied with kappa. That's the formula. Huh. Bacha, product of electrolysis is a very easy part. Okay? Do it on your own, and it's also absolutely theory. So forget about that. Okay? Alright guys, moving on. Next question is the conductivity of a 0.01 molar solution of acetic acid at 298 Kelvin is this. Conductivity is given. That means this is your kappa. Calculate the molar conductivity. How will you calculate? Lambda m is equal to 1000 multiplied with kappa divided by c. Again, same formula. No, Krisha, it's fine. Okay? It's fine. Same. Next question, shall we check it out? Next question is, once again, calculate the molar conductivity and degree of dissociation. Molar conductivity and degree of dissociation. Conductivity of this is the concentration of methanoic acid is this. Conductivity, kappa is given to you. Concentration is given to you. So how will you calculate lambda? Lambda m is equal to 1000 multiplied with 2.5 into 10 to the power minus ulta kar diya. One second, it will be 5.25 into 10 to the power minus 5 divided by 2.5. Yes, 2.5 into 10 to the power minus 4. So calculate this. Once you have calculated this, then you know that how do you calculate alpha? Alpha is equal to lambda m divided by lambda m naught. Okay. Yes. So from here you will calculate lambda m naught, and lambda m you will calculate from here. After that you can calculate degree of dissociation. Can you do this? You can do this? Yes? Chalo guys, with this note, I think we will have to finish it because we don't have any more time. We do not have any more time. In 5 minutes, your Durgesh Nandini ma'am, she will be here and she will teach you organic chemistry. So I'm going to end the session right now. It has been a very long session. Thank you so much to all the students who stuck till the end of it. I hope that you have understood what I taught you, and I hope that this session has really been beneficial to you. Okay. Extremely sorry for all the negative comments that come, and I do take it in my heart. I really can't help it. I'm a teacher and I'm a human that way. I am not a robot who cannot look at the chat box and just go on and on. That's not my way. So extremely sorry that the class does get a little disturbed, but I will try my best to not look at the chat even more. Okay? Alright, with this note everybody, tada bye-bye. Tomorrow I will be doing a session on previous year question. All previous year question, sample paper questions and model type of questions. Okay? So tomorrow you will be there. Yeah, tomorrow be there. I'll take a session. Tomorrow also, Sunday, I will take a session. Okay? Chalo guys, bye-bye, and I'll be sending you the note in the Telegram channel. See you guys.